The largest galaxy we've ever found is so big it breaks the way we talk about galaxies. Its stars fade out, but its influence keeps going. Stretch the map far enough, and edge becomes a guess. So when a galaxy spans millions of light years, or fires jets tens of millions more, are we measuring a city of stars? Or the shadow of dark matter, and what does largest even mean? Beyond the bright spiral postcards, the universe keeps its true scale in things that barely shine. In the faint outskirts, galaxy becomes a contested border, argued over by photons, gravity and time. Tonight's images begin with something deceptively familiar. A smooth, golden swarm of ancient stars, calm as a museum relic. Then the camera keeps pulling back, and the calm becomes unsettling, because the light refuses to end where intuition says it should. In the deep exposures, a galaxy's outer glow is not a wall but a gradient. What looks like empty space turns out to be a thin population of stars, a haze of globular clusters, and hot gas traced in X-rays, all moving to gravity's quieter music. At the centres of rich clusters, that music becomes a chorus, and the brightest galaxy sits in a crowd that never truly disperses. Stripped stars drift between neighbours. Tidal streams dissolve into a diffuse sea, and the question stops being how big and becomes who owns what. Because size in astronomy is rarely a single measurement, it is a choice of ruler. You can draw a boundary where starlight falls below a threshold, where orbits remain bound, where dark matter dominates the mass, or where radio emission still whispers across the void. Each ruler tells a different story, and each story carries a different kind of terror. One kind is quiet, the realization that a record-setting halo may partly belong to a galaxy cluster itself, and that our catalogue labels can hide a shared tidal history. The other kind is loud in a way our eyes cannot see. In radio light, some galaxies announce themselves with structures so vast that the host looks almost incidental. Jets and lobes stretching through intergalactic space like signatures written by supermassive black holes. To follow these giants, we have to abandon the comfort of sharp edges and simple rankings. We will use optical and infrared light to map starlight, X-rays to reveal hot gas and pressure, radio surveys to uncover relic plasma, and gravity itself, through motions and lensing, to trace the unseen scaffolding. Along the way, the documentary will return again and again to a single unsettling theme. The universe does not merely build larger galaxies, it erodes the very definitions we depend on. And when those definitions slip, the numbers that once felt authoritative start to behave like mirages, shifting with every deeper exposure. So the task is not to crown a winner and move on. It is to learn what largest can honestly mean in a cosmos where boundaries overlap, where environments bleed into identities, and where the most important structures are often the hardest to see. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We'll begin where our everyday sense of scale fails, then dissect what an edge is made of, from starlight to dark matter. After that, we'll enter the realm of record candidates and radio behemoths, until the idea of size resolves into physics, not a single number. We learn space by analogy, then the analogies fail without warning, because the universe refuses to stay inside our metaphors. A galaxy feels like a big island of stars, a luminous continent surrounded by dark ocean, until one example stretches so far that the word starts to wobble. Start with the Milky Way, because it anchors our intuition and quietly sets the scale for every comparison we make. Its stellar disk spans roughly 100,000 to 120,000 light-years across, depending on how you define the faint outer edge. In wide-field images, the disk is a pale, flattened lens, with spiral arms traced by blue star-forming regions and dust lanes. Our sun sits far from the centre, embedded in that disk, so even our home view is already biased by perspective. Yet that number is only the beginning of what size can mean, because the Milky Way is not only a disk. Surrounding the disk is a stellar halo, thinly populated, extremely faint, and difficult to map without deep surveys. Beyond that lies a much larger dark matter halo, inferred from how stars and gas orbit, not from direct light. Even in our own galaxy, the edge is not a line, but a gradual thinning into near darkness. Now place IC 1101 beside it, not as a rival city but as a different category, and the comparison immediately starts to strain. IC 1101 is a supergiant elliptical galaxy, the kind of system that looks smooth and featureless in ordinary images. Its light is dominated by old stars, so the colour leans toward gold and amber rather than the Milky Way's mottled blues. It sits so far away that it appears as a concentrated glow, yet its measured extent is anything but compact. Its visible stellar body is often sighted up to about 550,000 light-years across, which is several Milky Ways laid end-to-end with room to spare. That figure already implies a history of growth through mergers, because elliptical giants are built by accumulation rather than by delicate spiral structure. The claim gets stranger when you include its diffuse stellar halo, which can extend toward 4,000 light-years under certain measurement choices. The halo is not a bright rim that you can outline with confidence, but a fading gradient that challenges the limits of detectors. At that scale, comparisons stop feeling like education and start feeling like vertigo, because the mind loses its foothold. A 4 million light-year envelope is not just a bigger galaxy in the everyday sense. It is a structure that overlaps the distances between galaxies we treat as separate neighbours, and it forces us to ask what separate really means. When the outskirts are that faint, the question becomes less about geometry and more about interpretation. To make that concrete, define our neighbourhood in space, the region we casually treat as our cosmic hometown. The local group is the Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies bound together by gravity. It spans a few million light-years, depending on how you draw the edge and which dwarfs you count as members. In visual terms, it is not a tidy cluster, but a loose association, with two dominant spirals and many small companions drifting in complex orbits. This is where the unsettling claim appears in headlines and lectures. If IC 1101's extended envelope really reaches millions of light-years, it could encompass our entire local group. The phrase sounds decisive, almost like a simple overlay on a map, but astrophysics forces a question behind it. When we say encompass, are we describing a physical system, or a faint brightness profile that happens to extend across a large radius? What does encompass mean when the boundary is not a wall, and when the outskirts are defined by a threshold rather than a cliff? Does it mean stars you can count one by one, or light you can barely detect after hours of exposure and careful subtraction? Does it mean a gravitational domain where orbits are bound to a common potential, or a faint glow shared with a cluster? The word feels simple in conversation, yet it fractures into technical definitions the moment we try to measure it. The documentary's premise begins here, with a measurement that becomes philosophical, because the universe turns our categories into negotiations. The cosmos contains objects so large that size depends on definition, and definition depends on what you can observe. When the edge fades into noise, the argument becomes part of the data, because the uncertainty is not a mistake, but a feature of the phenomenon. IC 1101 also lives in a place where edges are naturally confused, and that environment matters as much as the galaxy itself. It sits at the centre of a dense galaxy cluster, a region packed with galaxies moving at high speeds through a shared gravitational well. In such places, galaxies interact, merge and shed stars, and the cumulative effect is a fog of starlight between the bright cores. The space between galaxies is not empty, and the light between them is not always owned. Astronomers have a name for that shared glow, and the term is as revealing as it is unsettling. Intracluster light is the diffuse starlight floating in a cluster, stripped from galaxies by tides, harassment, and repeated close encounters. Those stars can be unbound from any single galaxy, yet they still orbit the cluster as a whole. When you measure a giant halo, you must ask where the galaxy ends and intracluster light begins, because the transition can be gradual and physically real. This is why largest galaxy is not a single contest with a single ruler, even when the numbers look clean on a graphic. It is a tension between competing boundaries, each tied to a different physical component and a different observational method. The same object can be modest by one definition and record-breaking by another, without anyone necessarily being wrong. The disagreement often lives in the outskirts, where the light is faintest and the models are most sensitive. There is also a historical echo here, because astronomy has repeatedly expanded the meaning of galaxy as instruments improved. A century ago, even the existence of other galaxies was debated, and the island universe idea was still contested. As telescopes grew larger and photographic plates gave way to digital sensors, the faint outskirts of galaxies became visible in ways earlier observers could not imagine. Today, deep imaging and careful background subtraction reveal halos and streams that were once literally invisible, and that progress keeps reshaping our definitions. This chapter sets up two contenders and two ways of being enormous, without pretending they are the same kind of record. The first contender is IC 1101, a supergiant galaxy whose scale is tied to stars and halos, and to how faint a glow we can reliably measure. The second contender is a class of giant radio galaxies, where the stars are only the core and the true extent is written in plasma. Both challenge intuition, but they do it through different physics. Names like Alcyonius and Porphyrion signal a different kind of size, one that appears only when we listen to the universe in radio waves. These are galaxies whose influence stretches far beyond their visible starlight, through relativistic jets and radio lobes inflated over immense timescales. Their largest dimensions can reach tens of millions of light years, dwarfing their own stellar bodies by factors that feel almost absurd. In a single frame, the host galaxy can look like a dot, while the radio structure spans a cosmic landscape. That sounds like a trick, but it is real structure in real space, shaped by magnetic fields and energetic particles. A radio galaxy can look ordinary in optical light, then become colossal when you map its radio emission and trace the lobe's faint edges. The same galaxy becomes a different object when you switch wavelengths, because different wavelengths reveal different physical processes. What looks like emptiness in visible light can be filled with tenuous plasma that still radiates in radio frequencies. So the core question sharpens, and it becomes the thread that ties both contenders together. When galaxies grow to absurd scales, what exactly are we measuring, and what are we choosing to ignore? Are we counting stars, dark matter, gas, or the reach of energy launched from a central black hole? When we say big, do we mean massive, extended, luminous, or influential? To follow the argument, we need a shared toolkit, because astronomy is not one camera but a set of windows. Optical light traces the stars we can directly see, and it defines the familiar silhouette that feels like the real galaxy. In optical images, structure is intuitive: disks, bulges, elliptical profiles, and the dust lanes that carve through starlight. But optical light is also selective, because it favours the brighter parts, and can miss the faint outskirts where the boundary debate lives. Infrared light emphasises older, cooler stellar populations, and it can reveal mass where dust hides detail in the optical. In infrared, the glare of young blue stars fades, and the smoother background of long-lived stars becomes clearer. That matters for giant ellipticals like IC 1101, where the bulk of the starlight comes from aging populations. It also matters for measuring halos, because the signal is subtle and easily confused with a background sky. X-rays reveal something else entirely, and in clusters they often reveal the dominant baryonic component by volume. Hot gas fills the gravitational well and glows in X-ray light, outlining the environment that shapes giant galaxies and feeds their central black holes. That gas can reach tens of millions of degrees, so it shines not in visible light but in high-energy photons. In images, it appears as a ghostly extended cloud, sometimes with cavities and ripples carved by past outbursts. Radio observations complete the picture by revealing jets and lobes, which are not made of ordinary starlight at all. They map relativistic particles spiraling around magnetic field lines, often invisible in optical images and only indirectly hinted at in X-rays. In radio, a galaxy can become a multi-million or multi-tens of millions light-year phenomenon, with twin lobes that fade gradually into the intergalactic medium. The edges can look like smoke in a headlight beam, present, structured, and yet difficult to outline. Each band gives a different answer to the same question, and the answers can disagree without contradiction. How big is the galaxy if you count only bright stars, the parts that stand out clearly above the sky background? How big is it if you include faint halo light at the detection limit, where a tiny calibration error can change the inferred radius? How big is it if you include the dark matter halo inferred from gravity, which can extend far beyond any starlight? The right answer depends on what physical boundary you care about. Dark matter is the quiet complication that haunts every boundary, because it provides most of the mass but none of the direct light. The stars are the decoration on a much larger halo, and the halo is not directly visible with telescopes. Its edge is usually defined by a convention, like where the average density drops below a chosen threshold relative to the cosmic background. That convention is useful, but it is also a reminder that we sometimes draw borders for practicality, not because nature draws them for us. Gas adds another layer of ambiguity, because gas responds to pressure, heating, and stripping in ways stars do not. Some gas is bound to the galaxy, cooling and potentially forming new stars, while some is being pulled away by tides or ram pressure. Some gas belongs to the cluster medium, heated and stirred by the motions of galaxies and by energy injected from black holes. In dense environments, gas can be shared, heated, and redistributed until ownership becomes a model choice rather than an obvious fact. So the word galaxy starts to blur for a reason, and the blur is not just semantic. A galaxy is not one thing, but a bundle of components with different extents and different histories, layered on top of each other like overlapping maps. Stars, gas, and dark matter do not end at the same radius, and they do not always move as one. When we say largest, we are choosing which component gets to speak, and we are choosing which measurement uncertainties we can tolerate. This is why IC 1101 is both famous and controversial, even among people who agree on the basic observations. It is a plausible record holder in stellar size if you include a vast halo and envelope, measured down to extremely low surface brightness. Yet that envelope may overlap with intra-cluster light, and the measurement depends on how deep the imaging goes and how carefully the background is modelled. A small change in methodology can shift the claimed edge outward or inward by an enormous distance. It is also why giant radio galaxies feel like a challenge to the category itself, because they stretch the idea of what belongs to a galaxy. Their jets are launched from a central engine, likely powered by accretion onto a supermassive black hole, and they carry energy far beyond the stellar body. The lobes can extend far outside any reasonable stellar boundary, interacting with the surrounding medium and sometimes leaving detectable imprints in X-rays. If you count the lobes, you're measuring influence as much as membership, and that choice changes the story you tell. The documentary will run on 2 tracks that eventually collide, because the same universe produces both kinds of extremes. Track 1 asks how a supergiant like IC 1101 forms in a cluster, through mergers, cannibalism, and the slow build of a diffuse halo over billions of years. In that track, size is accumulated piece by piece, as smaller galaxies are absorbed, and their stars are redistributed into a smoother envelope. Track 2 asks how a black hole can drive jets that outgrow the host by orders of magnitude, turning a galaxy into the anchor point for a structure that spans intergalactic space. Both tracks force the same uncomfortable question, and the discomfort is part of the wonder. Where does a galaxy end when gravity, light, and energy each draw different borders, and when those borders shift with wavelength and sensitivity? At what point does a galaxy become a cluster phenomenon, or a radio structure anchored to a galaxy rather than contained by it? When we push to extremes, we discover that our labels are tools, not laws. We can test the local group claim as a thought experiment, not a headline, because it clarifies what is at stake. If you placed IC 1101's faint envelope over our neighbourhood, would it truly contain the Milky Way and Andromeda as parts of one system? Or would it merely overlap them in projection, a faint brightness profile laid across space without shared dynamics? The distinction matters, because astronomy is full of structures that look connected until you measure their motions. In astrophysics, contain can mean several things at once, and each meaning points to a different measurement. It can mean that stars are physically part of the same stellar halo, sharing a common origin in mergers and tidal stripping. It can mean that objects share a common dark matter potential, so their orbits are bound to one gravitational well. It can mean that the light is continuous above a chosen surface brightness threshold, even if the underlying dynamics are more complex. These meanings can agree in ordinary galaxies, then diverge dramatically at the larger scales. Those meanings do not always agree, especially at the extremes where the outskirts are tenuous and the timescales are long. A faint halo can extend far without being dynamically unified in the way we imagine, because the outer stars may be only loosely bound. A jet can extend far without adding mass, while still reshaping the surrounding medium through pressure and shocks. In both cases, size becomes a statement about detectability and physical impact, not just about material boundaries. So the opening mystery is not only how big these objects are, although the numbers alone are enough to unsettle the mind. The deeper mystery is why the universe produces structures that force us to negotiate definitions, as if nature is testing the limits of our categories. The largest galaxy might be a record, or it might be a boundary problem disguised as a record, an invitation to look more carefully at what we mean by an edge. When the outskirts fade into the background, the act of measuring becomes part of the story. From here, we narrow the focus to the ingredients that make any galaxy, because the rulebook must begin with components. Stars provide the familiar outline, but they are only one layer, and they can be redistributed by mergers into halos and streams. Dark matter sets the gravitational stage, shaping orbits and controlling how galaxies grow, even though it remains invisible to our eyes. Gas and plasma reveal the environment that can inflate or erase edges, especially in clusters where hot atmospheres and interactions dominate. Once we know what a galaxy is made of, we can ask which component deserves to define its size and why that choice matters for the records we claim. Then we can return to IC 1101 and the giant radio galaxies with a clearer set of rules and with a better sense of what the measurements actually represent. The next step is to build that rulebook from the inside out, starting with the matter we can see and ending with the structures we can only infer. Chapter 1 left us with a problem disguised as a record. IC 1101 sounds like a single number, yet every number hides a definition, and every definition quietly smuggles in an assumption. A galaxy is not one layer of stars with a clean shoreline, it is stacked components that fade at different rates, and each component suggests a different edge, especially when gravity keeps working long after the light becomes faint. Start with the part our eyes want to trust. Starlight is the familiar body, but even starlight comes in nested structures that overlap in projection, so what looks like one smooth glow can be several populations piled along our line of sight. In images, that overlap is deceptive. A camera collapses three-dimensional structure into a flat oval, and the brightest inner regions dominate our perception, even when most of the galaxy's area lives in the faint outskirts. In a spiral like the Milky Way, the disk and bulge feel like the main event. The disk is rotationally supported, thin compared to its width, and patterned by spiral arms that are really density waves moving through stars and gas. Those density waves are not rigid arms made of the same stars forever. They're traffic jams in the disk, regions where gas compresses, cools, and forms bright young stars that briefly outline the pattern. The bulge, by contrast, is rounder and hotter in its motions. Its stars move in many directions, and that random motion makes the bulge look like a small elliptical embedded in a disk. Bulges also carry clues about assembly. Some are classical, built by mergers and violent relaxation, while others are pseudo-bulges grown slowly by bars and disk instabilities that rearrange stars over time. In a giant elliptical, the whole system is a bulge-like spheroid. There is no obvious disk to announce an edge, and there is no sharp dust lane to tell you where the bright structure stops. Ellipticals are pressure-supported systems, not rotating disks with sharp truncations. Their stars are held up by velocity dispersion, meaning the support comes from random orbital motion rather than orderly rotation. That dispersion is measurable in spectra. Absorption lines broaden because stars move toward and away from us at many speeds, and that broadening becomes a kind of thermometer for the galaxy's gravitational depth. Their brightness typically follows smooth profiles that decline without a natural cutoff. Many are well described by a Cirsic profile, a mathematical curve whose index changes how steeply the light falls in the outskirts. A higher Cirsic index means a more concentrated core and a more extended tail. In plain terms, the same galaxy can look compact in the center, yet refuse to end gracefully in the outer regions. That smooth decline is the first warning. If the light falls continuously, the edge becomes a question of threshold, not a physical wall, and thresholds are chosen by humans with instruments that have limits. Astronomers often describe the central concentration as the spheroid. In a supergiant elliptical, the spheroid dominates the light and the mass in stars, and its inner regions can be so dense that stellar orbits are packed like traffic in a city core. At those densities, encounters still rarely involve literal collisions because stars are tiny compared to the distances between them. Yet gravity couples everything, so the collective field shapes orbits into a stable, slowly evolving equilibrium. Visually, the spheroid is what you see in a typical image. It is the bright, smooth oval that looks complete, even when it is only the inner portion of a much larger structure. If you watch the brightness stretch outward in a time-lapse of deeper and deeper exposures, the spheroid feels like a lantern in fog. The The core stays steady while the surrounding glow gradually reveals itself as a separate, larger architecture. Outside the bright spheroid sits the stellar halo. The halo is made of old stars spread thinly, often deposited by mergers and tidal stripping, and it can carry chemical fingerprints that differ from the inner body. Those chemical fingerprints matter because stars remember their birth conditions. Metallicity gradients, for example, can reveal whether the outer halo formed from many small satellites or from a few larger accretions. In practice, metals means everything heavier than helium, created by earlier generations of stars. A metal-poor outer halo implies many low-mass donors, while a richer halo suggests bigger galaxies were shredded and absorbed. The halo is not just faint, it is structured in ways that can be subtle, with shells, streams, and gradients that encode past collisions, even when those features have been blurred by time and orbital mixing. Those structures are the leftovers of tidal forces. When a smaller galaxy falls in, gravity stretches it, first into tails, then into arcs, and finally into a diffuse spray that slowly wraps around the host. Imagine a deep exposure where the sky is nearly black, and the galaxy seems to breathe outward. At the limits of detection, faint arcs and ripples can appear, like the wake lines behind a ship frozen into starlight. In the best data, the ripples can look like contour lines on a map. They hint at orbits, at timing, and at the direction of past infall even when the original intruder is long gone. Globular clusters orbit through these regions like durable fossils. They are dense star clusters that survive mergers and can trace the galaxy's outer potential because their compactness makes them resilient against tidal disruption. Their resilience is physical. A globular cluster's stars are bound tightly enough that the cluster can pass through changing tidal fields, losing some members at the edges while keeping a recognizable core. Globular clusters are also old. Many formed more than 10 billion years ago, so their orbits sample a galaxy's history across most of cosmic time. Their colours add another layer of information. Many massive galaxies host two broad globular cluster populations, metal-poor blue clusters and metal-rich red clusters, suggesting multiple formation epochs and multiple sources. Globular clusters extend farther than the bright starlight in many galaxies. Counting them can reveal an outer reach where direct surface brightness fails, and their numbers often correlate with the mass of the surrounding dark halo. In visuals, they are not a smooth glow at all. They are pinpricks scattered around the galaxy, an invisible swarm made visible only when you mark each point and watch the pattern emerge. Then there is gas, which does not behave like stars. In massive ellipticals and clusters, much of the baryonic volume is hot gas, heated to tens of millions of degrees by gravitational infall and shocks. At those temperatures, atoms are stripped of electrons and the gas becomes plasma. It radiates through Bremsstrahlung and line emission, a thin X-ray whisper that tells us where the mass is heated and settled. Hot gas halos glow in X-rays, not optical light. They can extend far beyond the bright stellar body, shaped by gravity and by feedback from black holes that inject energy into the surrounding plasma. That feedback is not subtle. Jets and bubbles from an active nucleus can carve cavities in the X-ray atmosphere, dark voids rimmed by brighter gas, showing where mechanical energy has pushed the plasma aside. The gas halo is both a boundary and a battleground. It can be stripped by the cluster medium or replenished by cooling flows and mergers, and its temperature profile can reveal where energy is being added or lost. In an X-ray view, the scene changes completely. The galaxy becomes a bright knot inside a larger ghostly atmosphere, and the edges are defined by temperature gradients rather than by starlight. All of these luminous components sit inside something larger and darker. The dominant structure by mass is the dark matter halo, a vast distribution that does not emit light but governs the motions of everything that does. Dark matter does not end where the stars end. Its influence can extend hundreds of thousands to millions of light years, depending on how the halo is defined and on whether the galaxy lives alone or inside a larger cluster. Here the documentary's hook becomes technical. The largest galaxy might be a boundary problem because galaxies are defined by gradients, and gradients do not announce where they should be cut. To measure any edge in light, astronomers confront surface brightness. Surface brightness is brightness per unit area on the sky, not total luminosity, which means a huge object can be harder to see than a small bright one. This is counterintuitive, so it is worth lingering on. If you spread the same number of photons over a larger patch of sky, each pixel gets fewer photons, and the signal becomes easier to drown in noise. A galaxy can be enormous in extent and still be nearly invisible at its outskirts. The light is spread so thin that it competes with the sky background, and in practice the sky is often brighter than the signal we seek. The background is not empty. It includes air glow from Earth's upper atmosphere, scattered light from bright stars, detector artifacts, and unresolved sources that mimic diffuse halos. Even the telescope itself can imprint patterns. Internal reflections and extended point-spread function wings can scatter light outward, creating a false halo unless the instrument is modelled with care. Those wings matter because bright cores are relentless. A tiny fraction of central light scattered to large radii can imitate a real envelope, so calibration becomes part physics and part forensic accounting. Deep imaging is therefore a subtraction problem. The faintest halos appear only after careful modelling of the sky and the instrument response, and after repeated checks that the halo is not a processing echo. This is why different studies can disagree without anyone being careless. Small differences in background treatment can move an isophote by vast distances because the outer profile is shallow and every small offset accumulates. Surface brightness also creates a psychological trap. A galaxy looks smaller in shallow images and larger in deep images, even when nothing physical changed, and our brains instinctively treat the brighter boundary as the true one. Astronomers formalize this with isophotes. An isophote is a contour of constant surface brightness, used to define an isophotal radius that can be measured consistently within one dataset. In a plot, isophotes look clean and authoritative. In the raw data, they are extracted from a field full of gradients, faint contaminants, and subtle instrumental signatures that must be understood before the contour means anything. An isophotal radius depends on the chosen threshold. Change the threshold and the galaxy's measured size changes, sometimes dramatically for ellipticals whose light profiles decline smoothly for a long distance. That dependence is not a flaw in astronomy. It is a reminder that light does not provide a single natural boundary in smooth systems, especially when the outer regions are built from debris rather than from an original tidy structure. Because thresholds are arbitrary, astronomers also use a different metric. The effective radius, Re, is the radius enclosing half the total light, a definition that sounds simple until you remember that total light requires extrapolation. Extrapolation is mathematical, not magical. You fit a profile to the measured light, integrate it outward, and estimate what lies beyond the last reliable pixel, while admitting that the answer inherits the model's assumptions. Re is powerful because it is less sensitive to the faintest outskirts. It allows comparisons across surveys, even when the outer halo is uncertain, and it ties directly to how concentrated the galaxy's light distribution is. Re is also limited. Two galaxies can share the same Re while having very different outer envelopes, especially if one has an extended CD halo that adds light far from the centre without changing the inner half much. This is where giant ellipticals become special. Many brightest cluster galaxies have extra light at large radii, beyond a simple profile, and that extra light can dominate the impression of size in deep images. That extra component can appear as a change in slope. The inner profile behaves one way, then the outer light declines more slowly, as if a second, broader structure has been layered on top of the first. That extra light is often called an envelope or a CD halo. It can be built from stripped stars and disrupted satellites over billions of years, and it tends to align with the cluster's overall potential rather than with the galaxy alone. The term CD has history behind it. In mid-20th century cluster studies, astronomers noticed supergiant ellipticals with diffuse, extended halos, and the label became a shorthand for central dominance and an unusually large envelope. The envelope blurs the line between a galaxy and its environment. In a cluster core, the environment is not a backdrop but an active component, constantly exchanging matter through tides, encounters, and slow accretion. Intracluster light is the name for that shared component. ICL is diffuse starlight bound to the cluster potential, not clearly to one galaxy, and it can contain a significant fraction of a cluster's total stellar mass. ICL is produced by tidal stripping, harassment, and mergers. Stars are pulled from galaxies and become a population orbiting the cluster as a whole, often with a spatial distribution that is smoother than the galaxies that donated them. In a visual sequence, the ICL is the faintest layer. It is a dim mist between galaxies, revealed only when the bright members are masked and the remaining glow is stretched until it becomes visible. When that mist finally appears, it changes the mood of the scene. The The cluster stops looking like separate islands and starts looking like one ecosystem, connected by a shared, almost oceanic background of stars. ICL can masquerade as the outer halo of the central galaxy. The surface brightness is similar, and the transition can be gradual, so the question becomes whether we are seeing a galaxy's outskirts or the cluster's shared stellar sea. So the edge question becomes a classification problem. At what radius do stars stop being members of the galaxy and become members of the cluster, when both are governed by gravity and both overlap in space? There is no universal answer, because membership can be defined in multiple ways. You can define it by light profiles, by kinematics, or by binding energy, and each definition is useful for a different scientific purpose. Light profiles ask what you can photograph. Kinematics asks what orbits what, an operational question that turns the galaxy into a dynamical system, rather than a shape on the sky. Kinematics offers one route. If you measure velocities of tracers, you can see whether they orbit the galaxy's potential or the cluster's potential, because the characteristic speeds rise as the cluster's mass begins to dominate. In the inner regions, motions reflect the galaxy's own gravitational well. Farther out, the velocity dispersion can climb toward the cluster value, hinting that the stars are no longer confined to the galaxy alone. But kinematics is expensive at great distances. For AC 1101 and similar systems, individual stars are not resolved, so we rely on tracers that can be detected as discrete objects against the sky. Planetary nebulae can act as tracers. They are bright emission line objects tied to old stars, detectable farther out than diffuse starlight, because a single nebula can outshine the local background at specific wavelengths. Their usefulness comes from physics you can hear in the spectrum. The O3 emission line is strong and narrow, so you can pick out a planetary nebula and measure its velocity with surprising precision. They are called planetary nebulae for historical reasons, not because they have anything to do with planets. Early observers saw small round disks in telescopes, and the name stuck even after the physics became clear. Globular clusters are another tracer population. Their spatial distribution and velocities can map the transition from galaxy-dominated to cluster-dominated dynamics, and their colours can hint at multiple formation channels. X-ray gas provides a different tracer. The temperature and density profiles of hot gas respond to the depth and shape of the gravitational well, and abrupt changes can signal where the cluster medium begins to overwhelm the galaxy's own atmosphere. Weak gravitational lensing provides yet another handle. It measures the statistical distortion of background galaxies to infer the mass distribution, turning distant galaxies into test particles whose shapes encode the foreground gravity. Lensing does not care about surface brightness. It can reveal the dark halo's extent even where there are few stars and little gas emission, and it can detect mass that is otherwise invisible to electromagnetic surveys. These methods do not always agree on a single radius. That mismatch is not confusion, it is the point, because different components have different edges and because the cluster environment makes those edges overlap. Astronomers therefore talk about multiple sizes. There is a size in light, a size in tracers, and a size in mass, and each one answers a different question about what the system is doing. The mass size is often defined with conventions like R200 or RVRM. These are radii where the average density reaches a chosen multiple of the cosmic critical density, a bookkeeping tool that connects observations to cosmological simulations. The critical density is a cosmological reference level, tied to the expansion rate of the universe. Using it turns a messy, gradual halo into a standardized definition, even though the real edge remains physically fuzzy. Those conventions are useful for simulations and comparisons. They also admit that the halo's edge is not a physical cliff in the dark matter, but a region where the halo gradually blends into the surrounding cosmic web. In isolation, a halo can be treated as a single object with a definable virial radius. In a cluster, halos overlap, and the idea breaks down, because the central galaxy's halo is embedded inside the cluster's larger, deeper halo. Cluster environments turn boundaries into statistics. The central galaxy's halo merges into the cluster halo, and separating them becomes model-dependent, requiring assumptions about profiles, equilibrium, and how matter is distributed. This is the second warning behind the headlines. The largest galaxy might be large because the cluster itself is being partially counted, and the measurement may be capturing a shared envelope rather than a single, self-contained object. To see why clusters complicate everything, step back to the scale of a galaxy cluster. A cluster is a gravitationally bound system of hundreds to thousands of galaxies, assembled over time as smaller groups fall together. In simulations, clusters grow like branching rivers. Filaments funnel groups inward, and the cluster's mass increases through repeated infill, with each event stirring the gas and reshuffling orbits in the core. Most of a cluster's baryonic mass is hot gas, not stars. Most of its total mass is dark matter, forming a deep potential well that heats in falling gas and accelerates galaxies to extreme speeds. Galaxies inside a cluster move fast, often thousands of kilometers per second. High speeds reduce gentle mergers, but they increase repeated close encounters, and those encounters can reshape galaxies without fully combining them. Those encounters are called harassment. They shake galaxies, strip stars and gas, and feed the diffuse intracluster light, leaving behind disturbed morphologies and truncated gas reservoirs. Mergers still happen, especially near the center where relative velocities can be lower. The central galaxy can grow by cannibalizing satellites that sink via dynamical friction, a process that turns orbital energy into heat in the surrounding matter. Dynamical friction is a slow gravitational drag. Massive satellites lose orbital energy to the background and spiral inward over time, and the timescale depends on mass, orbit shape, and the density of the environment. You can picture it as a wake in the dark matter. The satellite pulls on the background pulls back, and the net effect is a steady loss of momentum that turns a wide orbit into a slow inward fall. Each infall adds stars, globular clusters, and dark matter. It also puffs up the outer regions, building an envelope that is large in radius but low in brightness. So the galaxy grows outward, even when the center changes little. Tidal stripping adds a different contribution. Stars can be removed without a full merger, leaving streams and shells that later mix into a smooth halo, and that mixing can take billions of years to erase the evidence. Over billions of years, the cluster core becomes a recycling zone. Material is exchanged, redistributed, and partially unbound, yet still gravitationally organized, and the central regions become a layered record of repeated capture. This is why central galaxies and clusters are often the biggest by stellar mass. They sit where the supply of satellites is richest and the potential is deepest, so the odds of accretion and stripping are highest. It is also why their edges are hardest to define. The same processes that grow them also create ICL that blends into their outskirts, and the blend is not a mistake but a natural consequence of cluster assembly. Historically, this ambiguity has grown with our instruments. Early galaxy catalogues were built from photographic plates that missed the faintest outer light, and the galaxies looked like compact islands surrounded by darkness. Those plates had limited dynamic range and uneven sensitivity. Astronomers drew boundaries by eye and by plate limits, so the size of a galaxy often meant the size of what the emulsion could record. As detectors improved, astronomers began to see extended halos and CD envelopes. The definition of a galaxy's size expanded with sensitivity, and each new generation of imaging pushed the boundary outward. The shift was not only technological, it changed classification itself because galaxies once labelled normal ellipticals sometimes revealed extra envelopes when observed deeply enough. This is not merely a story of better cameras, it is a story of how measurement choices become physical claims when objects approach the detection limit, and how a contour on a plot can become a headline about cosmic scale. So we need a disciplined vocabulary before we return to IC 1101. We need to separate the bright spheroid, the faint stellar halo, and the possible CD envelope, because each one implies a different formation history. We need to keep globular clusters and planetary nebulae in mind as tracers. We need to remember that hot gas and dark matter extend farther than starlight, and that each component responds differently to the cluster environment. We also need to name the metrics we will hear later. Effective radius describes where half the light sits, not where the galaxy ends, and it often depends on how the inner profile is fit and how the outer light is extrapolated. Esophageal radius describes where the light drops below a chosen surface brightness. It is a practical boundary that depends on depth and calibration, and it can shift if the sky subtraction changes by a tiny fraction. Halo extent, inferred from tracers, describes where bound structures are still detected. It can reach farther than light, but it depends on sampling and modelling, and it can be biased by which tracers are easiest to observe. Dark matter halo extent describes where the mass profile blends into the cosmic web. In clusters, that blending is shared and cannot be assigned cleanly, because the central galaxy's halo is not an island but a peninsula. Now place these definitions back into the central question. When galaxies grow to absurd scales, what does largest mean, and which boundary are we measuring? Especially when different boundaries answer different scientific questions. If we mean largest by bright starlight, we will focus on isophotes and the inner profile. If we mean largest by half-light size, we will compare Re values, which are stable but can hide dramatic differences in outer structure. If we mean largest by stellar halo reach, we will rely on deep imaging and tracers. If we mean largest by mass halo, we will rely on dynamics and lensing, and we will accept that the result is statistical rather than photographic. Each choice answers a different physical question. Each choice also changes whether IC1101 looks like a galaxy record or a cluster boundary case, and that tension is exactly what makes the object so instructive. Before we name IC1101's home, we need an archetype. The Coma cluster is a benchmark for rich clusters and for giant ellipticals in dense environments, and it has been studied for decades as a nearby laboratory. Coma's role is partly historical. Because it is relatively close, it became a proving ground for techniques, photometry, spectroscopy, X-ray mapping, where astronomers learned how clusters hide mass and distribute light. Coma is nearby enough to study in detail and massive enough to be extreme. It contains two dominant central ellipticals and a sea of smaller members, all moving through a hot intracluster medium that fills the space between them. Coma also exhibits intracluster light and a hot X-ray atmosphere. It shows how a cluster's shared components can rival the galaxies themselves, and how the brightest galaxies can sit inside a glow that belongs to the cluster as a whole. In Coma, the central galaxies are not isolated islands. Their halos overlap with the cluster's diffuse light, and their dark matter sits inside a larger cluster halo. So even the concept of their outskirts becomes a careful statement. Coma teaches the lesson we need. In a rich cluster, the question is not only how big a galaxy is, but what belongs to it, and what belongs to the larger structure that hosts it. Now pivot from the archetype to the specific case. IC1101 is not in Coma, but it lives in a similarly dense, massive cluster environment, where the same physical processes operate with the same relentless patience. Its host cluster provides the conditions that build supergiant ellipticals, high-density supplies satellites, and the deep potential retains stripped material as diffuse light, so growth can continue long after the central regions appear mature. That environment also guarantees ambiguity. Any attempt to measure IC1101's outer halo must confront the possibility of intracluster light contamination, and must ask whether the faintest glow is bound to the galaxy or to the cluster. This is where the unsettling claim appears in headlines and lectures. A multi-million light-year halo sounds like a single object, but it may be a blended boundary, an observational contour drawn across a shared gravitational landscape. We can now state the chapter's foundation in one line. A galaxy's edge is not a line because its components end at different radii, and because the environment can add an extra layer that looks like part of the galaxy. The spheroid fades smoothly. The stellar halo extends farther, and it can carry the scars of mergers even when those scars are almost erased. Globular clusters and planetary nebulae can trace even larger scales. Their motions can reveal where the galaxy's influence weakens, and where the cluster's deeper potential begins to dominate the choreography. Hot gas halos can be larger still, shaped by the cluster medium. Dark matter halos extend the farthest, and in clusters they overlap into a shared structure, making ownership a matter of definition rather than a visible border. So when we ask for the size of IC1101, we must specify the ruler. We must specify the wavelength, the threshold, and the physical component, because each one draws a different map of the same underlying system. That specification does not weaken the mystery. It sharpens it, because it shows how an object can be simultaneously well measured and hard to define, and how the same data can support different defensible boundaries. From here, we narrow the focus from definitions to a single target. Now that the edge is ambiguous, we can meet IC1101 as the test case, and watch how each metric tells a slightly different story. IC1101 will force every metric to speak at once. Its bright body, its extended envelope, its tracer populations, and its cluster context will not align neatly, and that misalignment is the clue rather than the complication. And once we see that misalignment clearly, the phrase largest galaxy becomes what it always was. It becomes a question about physics, not just a number, and about where we choose to draw the edge of a fading, evolving structure. IC 1101 is not a lone record holder floating in clean darkness. It is a brightest cluster galaxy, sitting near the gravitational centre of a rich cluster more than 1 billion light-years away. In wide-field views, the scene looks almost calm, pinprick galaxies scattered across black, yet the centre is a crowded intersection. That placement is the first clue to its scale, because cluster centres are where gravity piles up history. In a cluster core, the deepest gravity well and the densest traffic of galaxies overlap, and the central galaxy becomes the natural sink. Matter does not fall in as a neat stream. It arrives in clumps, along filaments, and in waves of infell that repeat for billions of years. On the largest maps of the universe, clusters sit at the nodes of the cosmic web. Filaments of dark matter and gas feed them like rivers, and smaller groups tumble in along preferred directions. When those groups arrive, they do not simply add their mass. They bring their own internal motions, their own satellites, and their own tidal debris. Astronomers call these systems BCGs for a reason. They are statistical outliers built by environment, where time and crowding turn ordinary growth into relentless accumulation. In surveys, BCGs sit at the bright end of the luminosity function, and they often look smoother and redder than their neighbours, clues to old stars and long histories. That redness is not cosmetic, and it is not just about dust. It usually reflects stellar populations dominated by cooler, longer-lived stars, with star formation that peaked early and then faded. In plain terms, the light is telling us that most of the stars are old, and that the galaxy has been living off mergers more than new births. A BCG grows in 2 ways at once, and the two can be hard to separate in images. It gains stars through mergers and cannibalism, and it gains apparent size as stripped stars build a diffuse envelope. One process adds mass to the centre, while the other paints the outskirts with light so faint it almost vanishes. Those 2 channels also leave different signatures in the stellar orbits. The inner regions can be dominated by stars that have settled into a dense, pressure-supported core. The outskirts can be dominated by accreted stars on wider, more eccentric paths, which makes the profile look inflated even when the centre looks calm. IC 1101 is the extreme example that keeps returning in size debates. It forces the viewer to ask whether the largest galaxy is a single object, or a boundary drawn through shared cluster light. The question sounds philosophical, but it is also technical, because telescopes measure photons, not ownership. Start with the part we can state cleanly, even if the edges remain debated. IC 1101 is often framed as containing on the order of tens of trillions of stars, with some estimates reaching roughly 100 trillion. Even spoken aloud, that number resists intuition, because it is not just large, it is structurally different from a normal spiral. A spiral like the Milky Way organises much of its starlight into a thin disk. IC 1101, by contrast, is dominated by a swollen spheroid, where stellar motions are more randomised. When a system is built by repeated mergers, ordered rotation is harder to preserve, and the result is a smoother, rounder glow. That number is not a census, and it is never a count of individual suns. It is an order of magnitude statement inferred from luminosity, stellar populations, and mass-to-light assumptions that shift with model choices. A red, old population emits less light per unit mass than a young blue one, so the same brightness can imply very different totals. Even the initial mass function, the assumed distribution of stellar masses at birth, quietly shapes the answer. If a galaxy formed proportionally more low-mass stars, it can hide more mass in faint, long-lived dwarfs. If it formed relatively more high-mass stars, it would have shone brighter early, then faded as those stars died. Astronomers build those inferences from spectra and colours, which act like fingerprints of stellar age and metallicity. In giant ellipticals, the light is dominated by older, cooler stars, and the spectrum carries absorption features shaped by elements forged in earlier generations. The models then translate that integrated glow into a plausible stellar mass, but the translation is never perfectly unique. Metallicity matters because it changes how stars radiate at the same mass and age. A metal-rich population has more absorption lines and tends to look redder, which can mimic age effects if you are not careful. So observers combine multiple wavelengths and spectral indices, trying to break the degeneracy with careful modelling. Even the visible body is already beyond everyday intuition. Many studies cite a stellar extent up to about 550,000 light-years across for the brighter component. In images, that bright component reads as a smooth, pale oval, with a core that saturates quickly and wings that fade into a gentle gradient. The camera can linger on that gradient because it is where the eye begins to doubt itself. The inner light feels solid, like a marble lit from within, while the outer light becomes a thin veil. Each step outward is not a sharp boundary, but a softer and softer whisper. Put that beside the Milky Way's roughly 100,000 to 120,000 light-year disk, and the comparison becomes immediate. The Milky Way is a familiar city, while IC 11901's bright body is a sprawling metropolitan region. If you could float above it, the bright centre would look like a dense downtown, and the outer light like suburbs dissolving into haze. The scale also changes what structure means. A spiral like the Milky Way has arms, dust lanes, and star-forming regions that carve patterns into the disk. A supergiant elliptical is different. Its stars orbit in a more randomized swarm, and the overall shape is set by gravity's long averaging. That averaging is what violent relaxation does after major mergers. When gravitational potentials fluctuate rapidly, stellar energies are redistributed, and the system settles into a smoother profile. The result is not featureless because nothing happened. It is featureless because so much happened that patterns were erased. But the chapter's tension comes from what happens next. The bright body is only the inner map, and the outer map is drawn in light so faint it competes with the sky. The camera lingers on the edges, where the galaxy seems to exhale into darkness, and the boundary becomes a matter of patience. In deep measurements, IC 1101 is associated with a diffuse halo or envelope that can extend to around 4 million light-years. That number is not a hard edge, and it is not universally accepted. It is a claim about detectability and modelling, not a claim about a physical wall. To visualise what that means, imagine contour lines spreading outward like ripples. At first the contours are tight and confident, hugging the bright core. Then they widen, then fragment, and finally they begin to merge with the cluster's own faint glow. Different papers report different boundaries because they are not measuring the same thing. Some measure an isophotal radius at a chosen surface brightness, while others model a profile and extrapolate. The difference is subtle in bright galaxies, but in a cluster core it becomes the entire argument. An isophote is simply a contour of equal brightness, like a topographic line on a map. Choose a brighter contour and the galaxy looks smaller and more definite. Choose a fainter contour and the map expands outward, but the contour becomes fragile, because the sky itself is bright compared to the signal. At these levels, the measurement becomes a subtraction problem. A tiny error in sky background, scattered light, or flat fielding can shift the inferred edge by hundreds of thousands of light-years. The viewer should imagine subtracting a whisper from a whisper, and then asking what remains. Sky background is not a single number, and it is not perfectly uniform. Airglow, zodiacal light, and instrument glow can add gradients that change across the detector. Even in space-based imaging, scattered sunlight and detector effects can leave residual patterns that must be modelled away. Flat fielding sounds mundane, yet it is decisive at low surface brightness. Detectors have small sensitivity variations across their pixels, and optics add gradients that mimic real halos. If those patterns are not corrected, the outskirts can brighten or dim artificially, and a halo can appear where none exists. The cluster itself complicates every pixel. The background is not empty sky, because intracluster light adds a faint glow that can be mistaken for the galaxy's own outskirts. In a deep exposure, the space between galaxies is not black. It is a dim fog of stars stripped from countless encounters. Intracluster light is a kind of archaeological layer, spread through the cluster potential. It can form tidal streams, shells, and diffuse sheets depending on how galaxies were disrupted. Over time, those structures phase mix, and the cluster core develops a smoother, more pervasive glow, so the size claims arrive with an asterisk. The halo could be a true bound stellar component, or it could be a blend where galaxy light dissolves into the cluster's shared stellar sea. Either way, the light is real, but the label we attach to it is the unstable part. This is where the term CD galaxy matters. A CD is a central dominant galaxy with an extended low-surface brightness envelope that often aligns with the cluster potential. The label emerged from early studies of cluster centers when astronomers realized some galaxies were too big, too smooth, and too entangled with their surroundings to fit older categories. Historically, Those early photographic plates captured the bright cores well, but they struggled with the faint outskirts. When astronomers began pushing exposure times and improving calibration, the envelopes became harder to ignore. The CD category was a way of admitting that some galaxies were also cluster phenomena. The envelope is the signature, and it changes the shape of the light profile. Instead of a single smooth decline, the outer light profile can show extra light at large radii as if a second, broader component has been layered on. That extra is not decoration. It is a record of past disruption. In profile plots, the inner regions often follow a well-behaved curve, then the outskirts flatten compared to expectations. The flattening suggests stars on wider orbits, spread through a larger volume, and less tightly tied to the central density peak. In plain language, the galaxy's outskirts look puffed up by history. That extra component is physically plausible in a cluster core. Repeated mergers, tidal stripping, and the slow shredding of satellites can deposit stars far from the center. Some stars are tossed outward during violent interactions, while others are peeled off gently over many orbits. The gentle route is easy to miss, because it is not cinematic. A satellite can lose a small fraction of stars at each pericenter passage, leaving behind a faint stream that wraps and dissolves. Over time, many small losses add up to a vast, diffuse reservoir. The result is a galaxy that feels less like an island. It becomes a continent whose coastline is not a line, but a gradient that fades into an ocean of intra-cluster light. The visuals can emphasize this by letting the bright core hold steady, while the outer glow slowly emerges from the noise. To keep the viewer anchored, the chapter returns to light years as a repeated motif. Each step up in radius is a step up in meaning, from inner body to halo to cluster scale glow. Distance becomes a rhythm, and the rhythm becomes a way to feel the escalation. Begin with the Milky Way again because it calibrates the mind. About 100,000 light-years across is already hard to picture, yet it is still a compact silhouette compared to what follows. In a simple animation, the Milky Way can be a crisp disk, with a halo that is large but still contained. That halo is itself a reminder that edge is already complicated at home. The Milky Way's stellar halo extends far beyond the bright disk, and it contains streams from disrupted dwarfs. Even in our own backyard, the boundary is a gradient, not a wall. Then move to Andromeda, roughly 220,000 light-years across in stellar disk extent depending on definition. Even that larger neighbour remains a single, bounded-looking system in typical images. It has a recognisable edge in photographs, even though its own halo extends farther than the bright disk suggests. Andromeda's halo also carries scars, streams and shells that betray past accretion. Those features are visible because it is close enough for resolved star mapping. The same physical processes shaping Andromeda are at work in clusters, just amplified by density and time. Then widen to the local group, spanning a few million light-years depending on membership and boundary choice. At that scale, we stop talking about one galaxy and start talking about a gravitational neighbourhood. The frame now contains multiple major galaxies, dwarfs, and the empty-looking space that is not truly empty. The local group is held together by a shared gravitational potential, and its members are moving in slow, measurable ways. Some dwarfs are bound tightly to the Milky Way or Andromeda, while others drift in more extended orbits. The boundary is defined by dynamics, not by a visible glow. Now place IC 1101's claimed halo scale beside that neighbourhood. A 4 million light-year envelope is comparable to the local group's span, which is why the headline comparison feels so destabilizing. The viewer is meant to feel the mismatch between a galaxy and a group-sized number. But the documentary refuses to let the comparison stand as a simple overlay. The question is not only whether the numbers match, but whether the physics of membership matches. A boundary can be drawn in light, in gravity, or in history, and those boundaries do not always coincide. A local group boundary is usually a dynamical claim. It is about what is gravitationally bound together, and how galaxies move within a shared potential. Motions matter here. Radial velocities, proper motions, and the slow choreography of orbits over cosmic time. A halo boundary for IC 1101 is often a photometric claim. It is about how far a surface brightness profile can be traced before it merges with noise and cluster background. In practice, it is about how deep an observation goes, and how confidently the sky can be removed. Those two boundary types can agree in small systems. In a cluster core, they can diverge sharply, because light and gravity do not assign ownership in the same way. A star can contribute light centered on IC 1101, while orbiting in a potential dominated by the cluster's dark matter. So we keep scaling up, but we also keep tightening the definitions. IC 1101's inner body is a galaxy in the familiar sense, while its outer envelope may be a transition zone. The transition is not a failure of classification. It is a clue to how clusters assemble. The cluster environment explains why BCGs become extreme outliers. The central position gives them first access to infalling material, and dynamical friction helps massive satellites sink inward over time. In a sense, the cluster keeps delivering fuel to the center, and gravity keeps collecting it. Dynamical friction is slow but persistent, and it is easiest to picture as a wake. A massive galaxy moving through a sea of dark matter and stars gravitationally perturbs that sea, creating an overdense trail behind it. The trail tugs back, draining orbital energy and shrinking the orbit. The strength of that drag depends on mass and on the background density. In the crowded cluster core, the background is dense enough that the wake is substantial. Over long times, the effect turns the center into a merger factory, even when individual encounters are not spectacular. Over billions of years, that drag is transformative. It turns wide, looping orbits into tighter ones, and it increases the chance of close passages and eventual merging. The process is not dramatic in a single moment, but it is relentless across cosmic time. Not every encounter ends in a clean merger. Many interactions strip stars without fully combining galaxies, and those stripped stars become the raw material for halos and intracluster light. The stripping is strongest near pericenter, where tidal forces stretch and shear the smaller system. Tidal forces are simply gravity's gradient, and gradients tear things apart. The side of a satellite closer to the cluster center feels a stronger pull than the far side, and the difference can unbind stars. Those unbound stars do not vanish. They continue on new orbits, building a diffuse component that remembers the encounter. Some of those stars remain loosely associated with the central galaxy for a time, forming shells or broad fans. Others join the intracluster population, where their orbits are shaped more by the cluster than by any single galaxy. The same photons can look centered, while the dynamics tell a different story. This is why the central galaxy grows outward as much as inward. The core can remain relatively stable, while the outskirts expand through debris that settles into a broad, faint envelope. In simulations, the outer regions of massive ellipticals are often assembled late, built from accreted stars rather than in situ formation. In situ means stars formed inside the galaxy's own gas reservoir, near the center where densities were high. Ex situ means stars formed elsewhere, then arrived through mergers and stripping. In the bigger systems, ex situ growth can dominate the outskirts, which makes the halo a map of where the stars came from. The cluster's dark matter halo is the deeper stage beneath the visible drama. IC 1101's own dark halo is embedded inside the cluster halo, so the gravitational boundary is shared by construction. The galaxy sits like a bright ember inside a much larger invisible furnace. That shared halo changes how we interpret size. A galaxy's outer stars can orbit in a potential that is increasingly cluster-dominated, even if the light still appears centered on the BCG. The farther out you go, the less meaningful it becomes to say the star belongs to one galaxy alone. The cluster also contains hot intracluster gas, heated to tens of millions of degrees. It shines in X-rays and traces the depth and shape of the gravitational well. In X-ray maps, the cluster core can look like a luminous cloud, with brightness peaks and cavities that hint at energetic processes. That gas is not just hot, it is thin, like an ultra-high vacuum by Earth standards. Yet it fills an enormous volume, so its total mass is substantial, and its pressure shapes the cluster's internal weather. When the gas is disturbed, ripples and shocks can propagate for hundreds of thousands of light years. In that X-ray atmosphere, the central galaxy is not the whole system. It is a bright knot inside a much larger reservoir of plasma, pressure, and dark matter. The visuals can cut from optical starlight to X-ray glow, revealing that the cluster's dominant mass is not what the eye expects. The gas matters for growth and for limits. It can cool and feed the central regions, yet it can also be stirred and heated by feedback, preventing simple cooling flows. When the central black hole becomes active, it can inject energy into the gas, inflating bubbles and driving shocks that keep the core hot. Those bubbles can appear as dark cavities in X-ray images, like missing pieces punched out of the glowing atmosphere. Around them, Brighter rims can mark compressed gas, and faint ripples can mark sound waves travelling through the plasma. The cluster core becomes a laboratory where gravity and energy compete over long times. Even without lingering on the black hole, the consequence is clear. The cluster core is not a quiet pantry where gas steadily condenses into new stars. It is a regulated environment where heating and cooling compete, and where the BCG's growth is driven more by accretion of stars than by fresh star formation. The same environment that builds the BCG also erases clean edges. High-speed encounters, tidal fields, and repeated infall keep redistributing stars into a diffuse component that resists neat classification. The cluster is a mixing machine, and the central galaxy is where the mixture accumulates. Observationally, IC 1101's outer reach is inferred rather than directly outlined. Astronomers fit light profiles, trace isophotes, and compare models that include or exclude an extended envelope. The work is part astronomy and part careful accounting, because the signal is buried in systematics. The typical workflow begins with deep exposures that stack many minutes or hours of photons. Then comes masking, removing foreground stars, background galaxies, and detector artifacts that could contaminate the faint outskirts. Only after that can the outer light be measured with any confidence. Masking is more than drawing circles around obvious objects. The wings of bright stars can extend far, and faint background galaxies can hide inside the halo signal. Analysts often build masks iteratively, refining them after each pass when new faint structures become visible. Deep imaging is essential, but deep imaging is fragile. The faintest halo levels require careful sky subtraction, masking of background sources, and control of scattered light from the instrument. A single bright star just outside the field can throw stray light across the detector, creating gradients that masquerade as real structure. The point spread function becomes a hidden actor. Light from the bright inner regions can scatter outward, and if not modelled, it can mimic a halo that is not truly there. In other words, the telescope can paint a false envelope unless its optical fingerprints are understood. This is why modern analyses often model the PSF far beyond the core, using bright stars to measure the wings. Those wings can be faint, but they extend surprisingly far, and they matter precisely where the galaxy's own light becomes faint. The fight is between a real halo and an instrumental echo. The cluster background adds another layer of ambiguity. If intracluster light is not separated cleanly, the galaxy's measured size can inflate, because the profile never reaches a clear floor. The viewer should imagine trying to trace a shoreline while the tide and fog both rise. There is also the issue of where you center the measurement, because even center can be subtle. The brightest point in starlight may not perfectly match the center of the cluster potential traced by X-rays. Small offsets can matter when you're fitting faint, extended profiles across huge radii. This is why different studies can disagree without contradiction. They may be using different datasets, different thresholds, and different assumptions about where galaxy light becomes cluster light. Some analyses prefer conservative boundaries, while others explore the faintest plausible extensions, and both can be defensible. The uncertainty is not a footnote, it is the core of the story, because the largest galaxy claim is inseparable from the question of what we are willing to count. When the defining feature is faint, the definition becomes part of the measurement. IC 1101's light profile is unusual precisely because it tests those choices. The extended low surface brightness envelope is the feature that makes it a candidate for largest, and also the feature that blurs the category. It is a record of accumulation, but it is also a boundary dispute written in photons. If we define size by the bright stellar body, IC 1101 is enormous, but still recognizably a galaxy. The inner component is coherent, centrally concentrated and clearly distinct from the background in ordinary images. It behaves like a single object, even if its history is violent. If we define size by the faintest measurable envelope, it becomes a cluster-scale phenomenon. The outer light is so extended that it begins to describe the cluster's center as much as the galaxy itself. At that point, the word galaxy starts to mean the brightest peak in a shared glow. If we define size by gravitational dominance, the answer shifts again. The cluster potential dominates at large radii, so the outermost stars may be better described as orbiting the cluster than the galaxy. The stars can still be spatially centered on IC 1101, yet dynamically they may belong to something larger, so the chapter keeps returning to the same unsettling idea. The universe is not giving us a single edge. because the physics does not produce a single edge. In dense environments, boundaries are not walls, they are gradients shaped by repeated interactions. The viewer's mental map must expand in layers. First stars and the bright body, then the halo, then the envelope, then the intracluster light that makes the space between galaxies glow. Each layer is fainter than the last, and each layer is more communal. At each layer, the word galaxy becomes slightly less stable. The object remains real, but the boundary becomes a negotiated line between signal, noise, and physical membership. The narrator can pause here, letting the silence underline the discomfort of an answer that depends on definitions. This is the storm at the centre of which IC 1101 sits. The storm is not weather, but gravity, motion, and time, churning a cluster core until ownership becomes a gradient. In visual terms, the storm can be shown as slow orbital arcs, tidal streams, and a faint, pervasive glow. And it raises a quiet question that lingers under the measurements. When you look at a cluster core, are you seeing objects, or are you seeing a process frozen into light? If the outskirts are built from stripped stars, then the galaxy is also a history of loss. It is worth remembering that this way of thinking is historically recent. Early galaxy classification leaned on sharp photographic impressions, because plates captured the bright parts and missed the faint outskirts. As detectors improved, the universe quietly changed, revealing halos, envelopes, and intracluster light that had always been there. The shift was not only about better cameras, but about better calibration and better patience. Longer exposures, careful flat fields, and improved understanding of scattered light pushed the observable universe into fainter regimes. With that push, cluster centers stopped looking like clean collections of islands. The discovery of intracluster light itself reframed cluster centers. What looked like empty space became a diffuse component, and the central galaxy's envelope began to look like part of a broader stellar ecosystem. The more carefully we measure, the more the cluster core looks like a continuum rather than a set of separate islands. We can now restate the scale comparisons with the right caution. Milky Way to Andromeda is a step in disk size, Local Group is a step in neighbourhood size, IC 1101's halo is a step into definition itself. The numbers still astonish, but the meaning is now properly conditional, and that is why IC 1101 matters to the documentary's central question. When galaxies grow to absurd scales, largest becomes a choice between overlapping boundaries tied to different physics. The record is not just about size, it is about what we think a galaxy is when it lives at a cluster's heart. The chapter ends by tightening the suspense rather than resolving it. If IC 1101 is built by environment and time, we must ask how a galaxy gets that big. The question hangs, because the answer is not a single event, but a long chain of events. The answer is written in collisions, tides, and dark matter. The next chapter follows those forces and treats size as a history rather than a number. IC 1101 feels impossible because our intuition expects galaxies to have natural edges, like islands with shorelines and tidy coastlines. Cosmology expects the opposite, because gravity has no respect for borders and it keeps pulling, even when the pull is weak. In the standard picture, the universe builds large structures by assembling smaller ones, and the biggest galaxies become the bookkeeping of that assembly. They are not anomalies in the equations, but rather the most extreme receipts of a long cosmic transaction, paid in time, mass, and repeated encounters. Begin with the framework that quietly runs the whole story, even when the images look calm and the sky seems still. In LCDM, cold dark matter clumps first, then baryons follow the wells, because ordinary gas responds to gravity's scaffolding. Cold here means the particles move slowly compared with light, so they can collapse rather than stream away. More precisely, their low thermal velocities allow small-scale density peaks to survive the early universe without being erased. Dark means they do not emit or absorb light, so we infer them through gravitational effects instead, from galaxy motions to lensing distortions. The L is dark energy, a smooth component that accelerates cosmic expansion at late times, and it sets the overall timing. It does not build galaxies directly, yet it changes how long gravity has to work before expansion thins the supply. Within that timing, the early universe is a nearly uniform field with tiny density ripples, measured exquisitely in the cosmic microwave background. Those ripples are small, parts in 100,000, yet gravity amplifies them over billions of years, turning faint statistical noise into the architecture of everything we see. Small halos collapse early, then merge into larger halos, and the process repeats across cosmic time with a stubborn regularity. The reason is statistical as much as physical, because small peaks in the initial density field cross the collapse threshold first. As the universe expands, regions slightly denser than average slow their expansion, turn around, and fall inward. Dark matter halos virialize, converting infall energy into random motion, and they settle into a quasi-stable structure. In practice, virialization means the system reaches an equilibrium between kinetic energy and gravitational binding, even though the particles never collide. Baryons then shock, heat, cool, and condense inside those halos, but they arrive late to a stage already built. They also radiate, which makes them different. Gas can lose energy and sink, while dark matter largely cannot. This is hierarchical structure formation, and it is not a metaphor even if it sounds like one. Simulations show a branching growth tree where today's giants are made from many earlier, smaller ancestors. In those simulations, you can watch halos merge like droplets, while subhalos survive briefly as orbiting satellites. The paradox is emotional, not physical, because the physics predicts that extremes should exist. If you roll enough cosmic dice across enough volume, you eventually roll something that looks impossible. The real surprise is not that IC 1101 exists, but that we can see its faint outskirts at all. The cosmic web is the delivery system that makes hierarchy efficient, and it is visible in both theory and observation. Filaments connect dense nodes, and matter flows along those filaments into groups and clusters, guided by the geometry of the gravitational field. In computer visualizations, the web looks like luminous strands in a dark ocean, with knots where multiple strands intersect. Those knots become galaxy clusters, the largest bound structures in the universe, and they grow by eating the web itself. A brightest cluster galaxy is not fed from all directions equally, because the web channels supply along preferred routes. The feeding is anisotropic, and that directional bias leaves subtle signatures in galaxy alignments and infall patterns. Even the orientation of a central galaxy can remember the direction of the most persistent filament, an ancient arrow pointing toward its next meal. IC 1101 sits at a node where the supply chain never really stops, at least on human timescales and even on many galactic ones. The cluster keeps receiving groups, and groups bring satellites, gas, and dark matter, like cargo convoys arriving at a port. Even when the cluster looks mature, the cosmic web continues to deliver new material along filaments. The central galaxy grows because the environment keeps presenting it with material to absorb. The growth is slow enough to feel static, yet relentless enough to reshape a galaxy over billions of years. On screen, the cluster core can look serene, but the serenity is only the long exposure of a process that never truly ends. Now narrow from the cosmic web to the two ways a galaxy gains stars, because stars are the visible currency in this accounting. One channel is in situ star formation, where gas cools and forms stars inside the main progenitor. The other channel is ex situ accretion, where stars form elsewhere and arrive later through mergers or stripping. This distinction is not just bookkeeping, because it predicts different spatial distributions and different chemical fingerprints. In situ stars tend to live deeper in the potential well, while ex situ stars are often deposited at larger radii. It also predicts different orbital structures, because imported stars arrive with the memory of their original trajectories. In situ growth dominates early, when the universe is denser and gas is abundant, and cooling times can be short. Massive progenitors can form stars intensely, building a compact core quickly, sometimes in bursts that last only a few 100 million years. That early phase sets the central density and the old metal-rich population typical of giant ellipticals. Metal-rich, in astronomy, means enriched in elements heavier than helium, forged in earlier generations of stars. When star formation is rapid, supernovae enrich the gas quickly, and subsequent stars inherit that chemical maturity. The enrichment is not uniform either, because the deepest regions trap metals more efficiently. Another reason the centers of giant ellipticals look chemically older than their outskirts. The early core is also where the galaxy's stellar dynamics become established, because crowded conditions encourage violent interactions. Gas clouds collide, dissipate energy, and sink toward the center, where pressure and density rise. The result is a dense stellar body with little remaining cold gas, especially if energetic processes heat or expel it. When we later see a giant elliptical that looks smooth and red, we're often seeing the fossil of that early intense era. The smoothness is deceptive, because it is the smoothness of a system that has been thoroughly stirred. Ex situ growth dominates late, especially for the most massive ellipticals, and the timing matters in a measurable way. After the core forms, the galaxy's later mass and size come mostly from mergers and accretion, not from making new stars. The outskirts become a mosaic of imported stars, mixed until individual donors are hard to identify. Some accreted stars arrive in coherent streams, then phase mix into a diffuse glow. Over time, the outer halo becomes a palimpsest, written and rewritten by repeated infall. If you could pause the universe and peel back the layers, you would find a history of arrivals, each one fainter than the last. This split explains why giant ellipticals can be huge without looking young, and why their appearance can be deceptive. Their light is red because the main star formation happened early, then shut down as fuel became scarce or inaccessible. Their size keeps increasing because adding stars at large radii changes the profile more than the colour. A small amount of light spread over a vast area can dramatically expand a measured radius, even if the central brightness barely changes. The galaxy can grow outward like a fog bank, thickening at the edges rather than brightening at the centre. That fog is made of real stars, but it behaves visually like atmosphere, present, extensive, and easy to underestimate. To see this visually, imagine an image stretched to reveal faint structure that ordinary viewing hides. The inner body of a giant elliptical is bright and smooth, a concentrated oval that looks finished. Then, as the exposure deepens, a ghostly envelope emerges, extending far beyond the obvious boundary. The surface brightness drops so low that it competes with the sky background and instrumental scattered light. Measuring that envelope becomes a technical challenge, and the challenge itself becomes part of the story. Flat field errors, scattered starlight, and the glow of Earth's atmosphere can masquerade as halos, so observers must subtract with care. The most dramatic halos are therefore also the most fragile measurements, real but demanding. The next step is the kind of mergers that build a giant without reigniting it, because not all mergers are equal in their consequences. Gas-rich mergers can trigger starbursts, making blue light and new disks, because cold gas can compress and collapse. But cluster centers often deliver gas-poor galaxies, and the mergers become dry, like collisions of stellar systems rather than clouds. In dense environments, galaxies can lose gas through ram pressure stripping as they plough through the hot intracluster medium. They can also be strangled, cut off from fresh gas supply, so their remaining gas is used up and not replaced. Over time, the cluster acts like a drying wind, turning potential star formers into inert stellar systems before they ever reach the center. A dry merger is mostly stars and dark matter, with little cold gas to compress, and that changes the outcome. Without much gas, there is no dramatic new star formation, and the remnant stays red, dominated by older stars. The growth is structural, not luminous in the way a starburst would be, and the light profile changes subtly. The remnant's stellar orbits become more extended, and the galaxy's effective radius can inflate. In deep images, this looks like a swelling halo rather than a bright new core. The merger can be violent dynamically while remaining quiet photometrically, an event that rearranges stars without announcing itself in blue light. Repeated dry mergers have a specific geometric consequence, and simulations show it with striking consistency. They tend to puff up the remnant and expand the effective radius, because orbital energy is redistributed into the stellar component. The galaxy can double in size with a smaller increase in central density, because the added stars settle on wider orbits. This is not just adding mass, but rearranging phase space, which is the combined space of positions and velocities. The inner regions remain relatively stable, while the outskirts absorb much of the merger's dynamical heat. In practical terms, the center keeps its old character, while the edge becomes a growing archive of captured trajectories. This is why size and mass do not scale simply in the biggest systems, and why the largest ellipticals break naive expectations. Adding a satellite does not just add light, it redistributes orbital energy and angular momentum throughout the remnant. The outer profile becomes shallower, and the envelope becomes more prominent, even if the inner body changes little. Observationally, this can appear as a high Circic index profile, with extended wings that refuse to fade quickly. The galaxy's silhouette becomes less like a compact ellipse and more like a luminous atmosphere. When you look at the faintest contours, You're not seeing a clean boundary, you're seeing the memory of many orbits. In simulations, this is often described as inside-out growth, and the phrase is literal in radius. The core forms early and becomes relatively stable, because later mergers deposit most of their stars at larger distances. The outer regions keep being rebuilt by later accretion, which is why the outskirts are the best archive of mergers. If you could tag each star by birthplace, the centre would glow with a local origin, while the halo would glow with immigrants. That immigrant population can carry different metallicities and different orbital anisotropies, offering clues to the mass spectrum of past accretions. Massive donors leave broader, more metal-rich debris, while small donors contribute faint metal-poor light that is easy to miss. But mergers are only half the story, because not every infall ends as a clean coalescence with a single remnant. Tidal stripping can remove stars without fully merging the galaxies, especially when the satellite's orbit is fast and the cluster's tides are strong. Those stripped stars become diffuse halos and intra-cluster light, and they blur the boundary we keep trying to draw. The process is incremental, a little mass lost on each pass, until the satellite is whittled down to a core. Sometimes that core survives as a compact remnant, a dense nugget that hints at what was removed. In a sense, the cluster performs slow-motion erosion, shaving galaxies down as they circle. Tides are gravity's gradient, and gradients do damage over time, even when the overall force seems gentle. A satellite passing near the centre feels a stronger pull on its near side than its far side, and the differential stretches it. Stars at the satellite's edge become unbound first, then streams form, then the streams dissolve as orbits precess and mix. In a cluster, the background potential is complex, so streams can be rapidly scrambled. What begins as a thin ribbon becomes a faint, broad haze, hard to separate from other debris. The visual consequence is subtle, because the cluster hides its violence behind low contrast. The dissolved material does not vanish into emptiness, because the cluster is not empty space. It spreads into a low surface brightness component that can wrap around the central galaxy, following the combined gravitational field. Over billions of years, many small contributions add up to a vast, smooth-looking envelope, even if the construction was messy. In very deep exposures, intracluster light can show subtle asymmetries, shells or plumes, like smoke lingering after an unseen collision. Those features are time capsules because they fade as the stars mix. When you see a shell, you are seeing phase-wrapped debris, a geometric echo of a disrupted orbit. This is where IC 1101 becomes a boundary problem again, and the problem is both physical and definitional. The diffuse light around a BCG can be partly the galaxy's own extended halo, gravitationally bound to the central stellar system. It can also be intracluster light that belongs to the cluster potential more than any single galaxy, orbiting the cluster as a whole. The two components can overlap in projection, making them difficult to disentangle from a single image. Even with spectroscopy, the kinematics can transition gradually rather than abruptly, as if the universe refuses to draw a line. The velocity dispersion may rise outward, hinting that the stars are increasingly governed by the cluster rather than the galaxy. The distinction matters because it changes what largest galaxy means, and it changes the story we tell. If the envelope is mostly bound to the galaxy, it is a record of extreme assembly, a monument to mergers. If it is mostly cluster-owned light, then the record is about the cluster, and the galaxy is the brightest peak in a broader sea. When we quote a diameter or a stellar mass, we are implicitly choosing a definition of membership. That choice can shift the numbers, sometimes dramatically, especially when the light is faint and extended. The measurement becomes a negotiation between physics and convention, between what is there and what we decide to count. Historically, this ambiguity has followed astronomy for decades, because classification often lags behind discovery. Early galaxy catalogues were built from photographic plates, where surface brightness limits were harsh and faint halos were invisible. As detectors improved, galaxies grew in the data, not because they physically expanded overnight, but because our eyes became more sensitive. The same object can look modest in a shallow image and colossal in a deep one. IC 1101 sits at the extreme of that effect, where the outskirts are a test of both physics and measurement. The history of astronomy is full of such expansions, new instruments revealing that the universe was always larger than our thresholds. To understand why the peak sits at the centre, introduce the slow drag that turns satellites into meals, even in a fast-moving cluster. Dynamical friction is a gravitational braking effect, strongest for massive satellites moving through a dense background of dark matter and stars. The satellite raises a wake, a trailing over density in the background, and the wake pulls back on the satellite. It is a collective effect, like a boat creating a wave that then tugs on the hull. The heavier the satellite and the denser the medium, the stronger the braking. In the language of dynamics, momentum is transferred from the satellite to the background, and the orbit decays as the system seeks a new equilibrium. The result is a steady loss of orbital energy, and the timescale can be billions of years, not millions. Over time, the orbit shrinks, and the satellite spirals inward, especially if it is on an initially bound eccentric trajectory. In a cluster core, this process preferentially delivers the most massive satellites to the central galaxy, because small satellites experience weaker friction. That preference shapes the mass function of what gets accreted, and it helps explain why BCGs are so dominant. The center becomes a sink for the largest available pieces. It is cannibalism governed by statistics. Rare, massive prey is the most likely to reach the deepest water. Dynamical friction helps explain why BCGs occupy special real estate, and why that real estate is stable over long spans of cosmic time. They sit near the bottom of the potential well, where the background density is high and the gravitational field is deep. That position makes them efficient collectors, even when the cluster's high speeds suppress mergers elsewhere. In the outskirts of a cluster, galaxies can pass each other too quickly to merge, like ships crossing in a storm. Near the center, friction and repeated encounters slow the largest satellites enough to be captured. The cluster core becomes a place where encounters are not just frequent, but consequential. As satellites sink, they can merge, or they can be shredded before merging, and both outcomes feed the same reservoir. Either outcome adds stars to the central region's extended component, whether as a coherent addition or as diffuse debris. The cluster core becomes a recycling zone where galaxies lose material, and the central galaxy and intra-cluster light gain it. Over time, the distinction between galaxy growth and cluster-like growth becomes blurred, because both are fed by the same infall. The center becomes less a single object and more a luminous ecosystem. When we say IC 1101 is enormous, we may be describing the ecosystem's glow rather than a single organism. Now connect this to the observed structure of the biggest ellipticals, because morphology is the visible fingerprint of assembly. Their inner regions look smooth, because violent relaxation erased earlier patterns during major mergers, scrambling stellar orbits into a pressure-supported system. Violent relaxation is fast in dynamical terms, because the gravitational potential changes rapidly and stars respond collectively. Their outer regions look extended because later accretion deposits stars at large radii, where the surface brightness becomes fragile to measure. The inner light can be modelled cleanly, while the outer light depends on how deep you go and how well you subtract the sky. Observers often fit multiple components, because a single profile struggles to capture both the dense core and the diffuse halo. Each component is a clue, but also a reminder that our models are approximations laid over a continuum. In some giant ellipticals, the very center shows a core deficit, a shallow brightness cusp instead of a sharp peak. One leading explanation involves supermassive black hole binaries formed during mergers, which can eject stars through gravitational slingshots. That process scours out the central region, leaving a depleted core and a signature of past coalescences. The details vary, but the theme is consistent. Even the smoothest galaxies carry scars if you know where to look. IC 1101's scale invites the same question, because its center and its outskirts may have been shaped by different episodes. A galaxy can be calm in appearance while still bearing the fingerprints of repeated upheaval. The growth story also needs a mechanism that keeps the galaxy from simply forming new stars forever, because gravity alone would keep pulling gas inward. Massive clusters contain hot gas that should cool and flow inward, at least in naive expectations, because radiative processes allow plasma to lose energy. The intracluster medium is heated to tens of millions of degrees, glowing in X-rays, and it fills the cluster like a thin, luminous fog. At those temperatures, cooling can still occur, especially in dense cores, and early models predicted cooling flows that would feed star formation. Yet many BCGs are red and dead, with star formation suppressed, and the expected flood of cold gas is missing. The mismatch is one of the classic tensions that pushed astronomers to take feedback seriously. The key regulator is feedback from the central supermassive black hole, a compact engine that can influence a volume far larger than its event horizon. When gas tries to cool and fall in, the black hole can become active and inject energy into its surroundings. Jets and outflows inflate cavities in the X-ray gas, drive shocks, and stir turbulence, preventing a sustained cooling flow. In images from X-ray telescopes, these cavities can look like dark bubbles carved into a bright atmosphere. The bubbles rise buoyantly, transporting energy outward and mixing the medium. Radio observations often trace the same structures, revealing that the bubbles are filled with relativistic plasma that can persist long after the central outburst fades. This feedback does not need to be perfectly efficient to matter, because it acts over long times and large masses. It only needs to offset radiative cooling over billions of years, maintaining a rough thermal balance in the cluster core. The result is a galaxy that stops growing by in situ star formation, while still growing by accreting stars formed elsewhere. This is a subtle kind of growth because the galaxy changes size and mass without changing its stellar age distribution much. The system becomes an old city that keeps annexing suburbs, rather than building new neighborhoods from scratch. The annexations are quiet, but the map keeps changing. That combination produces the eerie stability of a giant elliptical, and it is part of the mystery on screen. The stellar population stays old, and the colour stays red, dominated by long-lived low-mass stars. The size still increases, because dry mergers and stripping keep adding material to the outskirts, where it barely affects the integrated colour. In a time-lapse of cosmic history, the centre would look almost unchanged after early times, while the halo would slowly thicken. The galaxy would appear to breathe outward, not by forming new light, but by redistributing existing light. The most dramatic change would be in the faintest contours, where the eye must be trained to notice growth. At this point, the chapter's tension sharpens into a single question. If IC 1101's visible envelope is built by a cluster's entire history, where does the galaxy end and the cluster begin? The answer depends on the invisible architecture underneath, because gravity decides what is bound and what is shared. The question is also philosophical, because our categories are human conveniences, not universal laws. Nature can produce continua where we prefer boxes. When you stare at the fading edge of the halo, you're also staring at the limits of language. Dark matter is the hidden ruler that sets the stage for every visible boundary, and it is the dominant mass component. The cluster's dark matter halo outweighs the stars by a large factor, and the BCG sits inside it like a bright ember in a vast furnace. At large radii, stars can be spatially centered on IC 1101 while dynamically responding to the cluster potential, orbiting as members of a larger system. In other words, the light can look galaxy-centered, while the gravity is cluster-centered. That mismatch is the heart of the boundary problem. It is also why the outskirts can feel uncanny, because they look like a galaxy, but behave like a cluster component. This is why the largest galaxy may be inseparable from its environment, especially in the densest nodes of the cosmic web. In a cluster, halos overlap, and the central galaxy's halo is embedded in a larger, deeper halo that extends far beyond the starlight. Ownership becomes model-dependent, because the gravitational field is shared, and the transition is gradual. One can define a galaxy by a surface brightness threshold, by a binding energy criterion, or by a kinematic transition, and each yields a different edge. IC 1101 forces those definitions to reveal their assumptions. It also forces a practical question. How faint a glow must be before we stop calling it part of an object? Observers map that invisible field in several ways, and each method illuminates a different aspect. Galaxy velocities and dispersion profiles trace the depth of the potential, because faster random motions imply a stronger gravitational well. Spectroscopy can measure redshifts of many member galaxies, building a statistical map of the cluster's mass distribution. Hot gas in X-rays traces pressure support and temperature gradients, which respond to the same mass profile. Under hydrostatic equilibrium assumptions, the gas can be used to infer the underlying gravitational potential, though mergers and turbulence complicate the picture. Even small departures from equilibrium can bias mass estimates, which is why multiple methods are compared rather than trusted alone. Gravitational lensing provides a more direct mass map, because it uses gravity itself as the measuring instrument. Weak lensing measures the statistical distortion of background galaxies, a subtle shear that requires many sources and careful calibration. Strong lensing can reveal dense cores through arcs and multiple images, where the mass is concentrated enough to produce dramatic distortions. Lensing does not care about surface brightness, so it can outline mass where light is faint or absent. In a sense, lensing is the universe drawing its own contour lines, independent of what shines. When those contour lines are overlaid on optical images, the mismatch can be striking, mass extending beyond the last visible isophotes like an unseen coastline. These mass maps often show that the cluster halo is the dominant structure, and the BCG is a luminous concentration inside a much larger distribution. When we claim a multi-million light-year halo in starlight, we are brushing against a halo defined by dark matter, whose scale is set by cosmological collapse. The stars are tracers, not the main mass, and their distribution can be shaped by processes that do not affect dark matter the same way. Dark matter remains collisionless and largely indifferent to gas physics, while stars remember dissipation, feedback, and stripping. The result is a layered system where different components tell different parts of the story. The light tells you where baryons ended up, while lensing tells you where gravity is strongest. So the growth story becomes a layered architecture with nested structures and nested timescales. The cosmic web feeds the cluster, and the cluster feeds the center, delivering satellites along preferred paths. Dry mergers and stripping build a diffuse stellar envelope, and dynamical friction keeps delivering massive satellites inward. Black hole feedback keeps the system from reigniting as a star-forming disk, maintaining a hot atmosphere that resists cooling. Dark matter sets the potential that makes the whole process coherent over billions of years, holding the system together even as its visible boundaries blur. The result is a giant that is both a galaxy and a cluster phenomenon, depending on the boundary you choose. The deeper you look, the more the categories overlap. This is the paradox resolved in one sentence, but the resolution has texture when you linger on it. Galaxies are not supposed to be this big under simple intuition, yet hierarchical cosmology expects the biggest nodes to accumulate extreme outskirts. IC1101 is what that expectation looks like in photons, stretched across an exposure deep enough to reveal the faintest light. It is not a single event frozen in time, but a cumulative outcome of many quiet events. The universe rarely builds its largest structures with a single dramatic gesture. It prefers accumulation, small changes that only become shocking when you add them up. But the chapter also leaves a deliberate discomfort, because the boundary question does not yield a satisfying line. If the outer light is partly intracluster, then largest galaxy is partly a naming choice, a label placed on a gradient. The universe is not offering a clean edge, because the physics does not create one, and the cluster's gravity does not stop at a convenient radius. When we insist on a border, we reveal more about our definitions than about nature. The faint glow around IC1101 becomes a reminder that categories can be porous. It also becomes a reminder that the deepest images are not just prettier, they're conceptually disruptive. From here, the documentary pivots to a different kind of boundary. IC1101 stretches the definition of a galaxy through starlight and shared halos, where size is measured by faint photons and uncertain membership. Another class of objects stretches it through influence, where jets redraw the map of what one black hole can touch. Giant radio galaxies will shift the ruler again, because their reach is not a halo of stars but a network of energy. Their stars may not be exceptional, but their reach is measured in magnetic fields, shocks, and long-lived plasma. The next chapter follows that reach outward, until size becomes a story about contact, not containment. We have been measuring giants by starlight, by halos, and by contested ownership, and each method has felt strangely human. Now the ruler shifts to something colder, less intuitive, and far more expansive than any stellar boundary. Some galaxies look ordinary in optical light, their stars arranged in familiar ellipses or disks, yet they dominate space through radio-bright structures powered by a central engine. In visible images, the host can seem almost modest, but in radio it becomes a machine that draws lines across intergalactic darkness. Radio galaxies are active galaxies whose cores are fed by accretion onto a supermassive black hole, and that feeding is the essential trigger. Gas does not simply fall straight in, because angular momentum forces it to spiral and flatten into a rotating accretion disk. Friction, turbulence, and magnetic stresses heat the plasma, and the disk radiates as gravitational potential energy is converted into light and motion. The black hole's gravity sets the stage, but the energy release comes from matter losing orbital energy, an everyday idea scaled up to a cosmic furnace. An active galactic nucleus is not a separate object, but a phase of a galaxy's life, and that distinction matters for how we think about size. When fuel reaches the centre, the nucleus can outshine the host across many wavelengths, from infrared to X-rays. Dust can hide the core in optical light, while high-energy photons leak out through polar regions and scatter into view. In radio galaxies, the most dramatic signature is not the core's glare, but the jets and lobes it drives, structures that can dwarf the galaxy that launched them. The radio emission is synchrotron radiation, from relativistic electrons spiraling in magnetic fields, and it has a distinctive physical fingerprint. The electrons move near light speed, and their curved paths force them to radiate strongly at long wavelengths, producing a broad, smooth spectrum. Polarization is often strong because the radiation remembers the geometry of the magnetic field that guided the particle's motion. When astronomers map spectral index and polarization together, they are not just making pictures, they are diagnosing particle energies and field order. Synchrotron emission is why these systems can look faint in optical images yet blaze in radio maps, as if two universes overlap on the same sky. The stars trace where the galaxy is, but the radio traces where the energy went, and those are not the same thing. That difference is the first crack in the idea that a galaxy's size must be a stellar boundary. It also raises an uncomfortable question. If energy can travel farther than matter remains bound, which footprint feels more real? Relativistic jets begin close to the black hole, in a region we cannot image directly from most sources, and the invisibility is part of the mystery. The accretion disk rotates at tremendous speed. Magnetic fields twist like elastic cords, and plasma is accelerated outward along field lines. The jet is not a simple stream of gas, but a magnetized outflow carrying energy, momentum, and ordered fields. Near the base, the flow may be Poynting flux dominated, meaning the electromagnetic field carries more energy than the particles do. Two ingredients matter for launching and sustaining jets, and both are easy to state even if the details are complex. The disk supplies magnetized plasma and a rotating platform that can wind fields into a tight structure, like a dynamo that refuses to stop. The spinning black hole can also contribute, with rotational energy extracted through magnetic connections that thread the horizon. In that picture, the black hole is not merely swallowing material, it is acting as a battery, and the jet is the circuit. Collimation is the key to the jet's unsettling reach, because without it the outflow would disperse and fade quickly. Magnetic pressure and hoop stresses can pinch the flow, keeping it narrow while it accelerates and stabilizes over many orders of magnitude in scale. External pressure from surrounding gas can also help confine the jet, shaping it like a nozzle on cosmic scales. The result is a beam that stays surprisingly disciplined, even while crossing a medium that is never perfectly smooth. The jet stays narrow because it is not just ballistic matter, but a flow dominated by field structure and internal energy, and that changes how it responds to obstacles. Instabilities do grow, and the jet can wobble, knot, or flare, leaving bright shocks that look like beads on a wire. Yet for the most powerful systems, the jet remains coherent long enough to cross distances that dwarf the host galaxy. When it does, the jet becomes a kind of cosmic handwriting, thin strokes that reveal where the engine has been. Relativistic effects matter, but they do not need to be treated as math to be felt, because they change what we think we are seeing. Near light speed, time and brightness become angle dependent, and one jet can look brighter than its counterpart even if they are intrinsically similar. Beaming can hide or exaggerate structures, complicating any simple picture of symmetry. It can also make the core appear more active than it is, because the jet points toward us like a flashlight. At the ends of many jets, the flow slows and dumps energy into large lobes, and the transition is often violent. These lobes are reservoirs of relativistic particles and magnetic fields, inflated like bubbles in the intergalactic medium and edged by weak shocks. Hotspots can mark where the jet terminates, while older plasma fades into faint diffuse edges that are easy to miss. In deep radio images, the lobes can look like ghostly wings, with brightness gradients that trace the history of injection. This is the other kind of giant, because the lobes can extend far beyond any plausible stellar halo, and they do it without adding a single star. A galaxy's stars might span tens or hundreds of thousands of light years, depending on how faint a halo you count. Its radio structure can span millions, and in rare cases tens of millions, turning influence into geometry. The scale is so extreme that the host galaxy can appear as a small marker pin at the centre of a vast faint figure. Astronomers call the largest examples giant radio galaxies, and the name is both descriptive and slightly misleading. The category is defined by projected linear sizes of order 1 million light-years or more, measured from lobe to lobe in the plane of the sky. The definition is observational, but the implication is physical, because it demands long-lived, stable energy delivery. A jet that flickers out quickly cannot inflate a structure that large, no matter how bright it becomes in the moment. Giant radio galaxies are not just bigger versions of common radio sources, because the scaling is not linear, and the obstacles change with distance. They are the outcome of a jet that survives, stays collimated, and keeps pushing into a medium that does not stop it. Their size is a negotiation between engine power, lifetime, and environment, and each term can dominate in different systems. A powerful jet in a hostile environment can end up small, while a moderate jet in a forgiving environment can become enormous. Environment is decisive because the jet's enemy is density, and density is not evenly distributed in the universe. In a dense cluster core, jets can be disrupted, bent, or smothered by pressure gradients and turbulent motions in hot intracluster gas. Ram pressure can sweep the lobes back, producing narrow-angle tails that look like windsocks. In lower density regions, the jet meets less resistance, so it can propagate farther before losing coherence. The same engine can therefore build radically different footprints depending on where the galaxy lives. Low-density environments also reduce radiative and adiabatic losses in a practical observational sense, because the lobes can expand more gently. The plasma does work on its surroundings as it inflates, and that expansion cools the electrons, but violent mixing can cool them faster. When external motions are weaker, the lobes can avoid being shredded into unrecognizable filaments. The result is a structure that can remain detectable as a faint radio glow long after the core's most violent phase. In some cases, the lobes persist as relics, even when the central engine is quieted. This is where the documentary's earlier boundary problem returns in a new form, and the shift is subtle but profound. IC 1101 blurred galaxy and cluster through shared starlight and shared gravity, and the argument turned on what belonged to what. Radio giants blur galaxy and intergalactic space through a footprint that is not made of stars at all. The boundary is drawn in plasma, and plasma does not respect the same ownership rules as starlight. The physics is different, but the discomfort is the same, because both cases force us to choose a threshold. A stellar halo fades because stars thin out, and we argue about surface brightness limits, binding and contamination from the cluster. A radio footprint fades because plasma ages, fields weaken, and surface brightness drops below survey limits. In both cases, the edge is not a wall, it is a gradient that depends on how hard we look. To understand why these objects were missed, we need the observational constraint that punishes all diffuse structures, no matter how large their total power. Surface brightness dimming grows severe with distance, and extended emission spreads across many beams, diluting signal into noise. A giant can be present in total flux, yet invisible in a shallow map, because the light is smeared thin across the sky. This is the cruel trick of the universe. The bigger the structure, the easier it is to overlook. Modern low-frequency radio surveys changed the search space, and they did it by embracing the faint and the wide. Arrays like LOFAR map large areas with sensitivity to diffuse, steep spectrum emission that older surveys struggled to capture. Low frequencies are especially good for older electron populations, which radiate more strongly there as higher energy electrons fade. In a sense, low-frequency maps are time machines, because they reveal plasma that has been cooling for tens of millions of years. There is also a historical arc behind this shift, because radio astronomy has always advanced in leaps of technique. Early surveys revealed bright classical doubles, and the sky was suddenly filled with galaxies that had invisible wings. Later, higher resolution instruments sharpened cores and hotspots, but sometimes filtered out the very diffuse emission that makes giants giant. LOFAR and similar arrays reopen that missing parameter space, combining wide-field imaging with sensitivity to large angular scales. The giants were not necessarily rare, our tools were simply tuned to a different kind of radio universe. The workflow is patient and statistical because the sky is crowded and the signals are subtle. Surveys build wide mosaics, then algorithms and human inspection search for paired lobes, faint bridges, and the telltale symmetry of a bipolar outflow. Cross-matching with optical and infrared catalogues identifies the host galaxy near the midpoint, anchoring the radio structure to a plausible engine. Spectroscopic redshifts, when available, lock down the distance, turning angles on the sky into millions of light years. Each identification is a small act of detective work, performed at the scale of the cosmic web. Selection effects shaped earlier catalogues in predictable ways, and the patterns are now easy to see in hindsight. High-frequency surveys favoured compact, bright cores and hotspots, not faint-aged lobes that have steep spectra. Limited angular resolution blended diffuse emission into the background, while limited sensitivity erased the lowest surface brightness edges. Even when lobes were detected, their full extent could be truncated by noise, making a giant look merely large. The catalogue became a mirror of the instrument, not a neutral census of nature. There is also a geometric bias that hides the most extreme systems, and it is almost embarrassingly simple. If a giant is oriented partly along our line of sight, its projected size shrinks, and the structure looks less dramatic than it truly is. If its lobes are asymmetric or one side fades faster, the system can be misclassified as unrelated patches. The universe does not arrange its biggest structures for our convenience, and projection turns true monsters into ambiguous smudges. With these tools, astronomers began finding giants that force a new scale comparison, and the surprise is that the hosts are not always extraordinary. The host galaxies are not always the most massive or luminous in starlight, and some look like fairly typical ellipticals. The record is set by the reach of the jet, not by the number of stars. That inversion is the chapter's quiet provocation, because it separates big from bright in a new way. Introduce Alcyonius as the first escalation point, and let the visual do some of the work. It is a record-breaking giant radio galaxy, with a projected extent of roughly 16 million light-years, depending on adopted cosmology and measurement. On a radio map, its lobes stretch like pale continents, with the host galaxy sitting near the centre as a small, bright dot. That span is so large that the host stellar body becomes a footnote to its radio map. The galaxy does not look like a giant in optical light, yet it behaves like one in the language of plasma. Alcyonius implies a central engine that stayed active, or repeatedly reactivated, over an immense timescale, and that implication is not optional. Jets must deliver energy for tens to hundreds of millions of years to inflate lobes that far, even if the power is not extreme at every moment. The system also implies a path through relatively forgiving intergalactic terrain, where the jet avoided catastrophic disruption and maintained collimation. It suggests a kind of cosmic luck, where geometry, environment, and engine all align long enough to build something enormous. We are watching persistence made visible. The existence of Alcyonius reframes what we mean by a galaxy's lifetime of influence, because it separates dynamical time from impact time. A star can orbit the galaxy for billions of years, but it does not reshape intergalactic space beyond the reach of gravity. A jet episode can be brief by cosmic standards, yet it can redraw the environment on scales comparable to galaxy groups. The jet is a transient event with permanent consequences, and that mismatch is part of what makes radio giants feel uncanny. The chapter's tension comes from what happens next. If 16 million light-years is possible, then the ceiling is not set by our intuition, or by the scale of stellar halos. The ceiling is set by how long an engine can run, and how empty the surrounding space can be. It is also set by whether we can see the faintest edges, where the plasma has cooled into near silence. The record, in other words, is partly a property of the universe, and partly a property of our maps. Now introduce Porphyrion as the second escalation, and treat it as a definitional shock that forces the viewer to recalibrate. Porphyrion's radio structure spans about 23 million light-years from end to end, a number that feels like it belongs to cosmology rather than galaxies. The lobes are so extended that they begin to resemble a segment of the cosmic web, drawn with a faint non-thermal ink. That distance is not a galaxy-sized number in any optical sense, yet it is still tied to one central black hole. The mind resists the connection, and that resistance is the point. Compare that span to the Milky Way's diameter, roughly 100,000 to 120,000 light-years for the bright disk, and the contrast becomes almost absurd. Porphyrion's footprint is about 140 times larger than the Milky Way's stellar diameter, and the ratio is meant to feel wrong. The comparison crosses category lines, because it pits a familiar spiral disk against a structure that is mostly empty space, filled with magnetic fields and relativistic particles. If you plotted both on the same scale, the Milky Way would look like a speck near the centre of Porphyrion's reach. Then compare it to the large-scale texture of the universe, because that is where the number begins to sound less like a record and more like a warning. Cosmic voids can span tens of millions of light-years, with filaments and walls outlining their edges in a foam-like pattern. If a jet system approaches a significant fraction of a void scale, it begins to look like a web feature, not a single galaxy's appendage. The jet becomes a bridge across the emptiest regions, and the emptiness is what allows the bridge to exist. This is the unsettling idea the chapter must land, and it lands slowly because it rewires our intuition. A galaxy's size might be dominated not by where its stars end, but by where its central engine has touched. The galaxy becomes less a city of stars and more a generator whose influence is written into intergalactic plasma. The radio map becomes a record of contact, showing where energy has been deposited into space that was never bound to the galaxy. If influence can be mapped, does influence become a kind of size? But we cannot accept the number without asking what exactly is being measured, because radio size is not an absolute property. Radio size is typically lobe-to-lobe extent above a detection threshold in a given map, and that threshold is a human choice. Change the threshold and the boundary shifts just as it does for faint stellar halos. Even the definition of where a lobe ends can depend on deconvolution, background subtraction, and how aggressively diffuse emission is recovered. The edge is partly astrophysics and partly methodology. Radiolobes also age, which means the edge is time-dependent, and the physics of that aging is well understood. Electrons lose energy through synchrotron radiation, an inverse Compton scattering off the cosmic microwave background, and both processes drain the highest energy particles first. As they cool, the emission shifts to lower frequencies and becomes harder to detect, even if the plasma remains present. The lobe can therefore be physically large while observationally smaller, like a fog bank that thins at the edges. What we see is not the full structure, but the part still bright enough to announce itself. Inverse Compton losses become more punishing at higher redshift, because the CMB energy density rises sharply with redshift, scaling as the fourth power of expansion. That makes distant giants harder to see in radio, especially at higher frequencies where only the highest energy electrons contribute strongly. The universe itself becomes a brighter loss field for relativistic electrons, and it accelerates their fading. This is a cosmic selection effect built into the background radiation of the universe. It means the farthest giants may exist yet be nearly invisible to us. So Porphyrion's discovery is not just a record but a statement about instrumentation and bias, and it carries an implied rebuke. If we can now see structures this faint and extended, then the census of giants was incomplete, perhaps dramatically so. The largest examples were not absent, but hidden below the surface brightness floor, waiting for the right frequency and the right sensitivity. The record holder is also a reminder that discovery is often a negotiation between nature and technology. We did not make Porphyrion larger, we made ourselves better at noticing it. The chapter's middle beat is a careful return to basic AGN physics, because the scale depends on the engine's bookkeeping, not just on our awe. Accretion converts gravitational potential energy into radiation and mechanical power, and the efficiency can be startlingly high. A small amount of mass fed steadily can supply enormous energy over long periods, because relativistic gravity makes the inner disk a deep energy well. In practical terms, the engine can run on a trickle, and still reshape a volume of space that dwarfs the host. The question becomes not whether the black hole can pay the bill, but whether it can keep the fuel line open. The black hole does not need to be large by record standards to produce a giant footprint, and that is another inversion of expectation. What matters is the combination of mass, spin, magnetic flux, and fuel supply, and each term can compensate for the others. The jet power can be a significant fraction of the accretion power, and in some regimes it can dominate the energy output. Observationally, that means a galaxy can look unremarkable in starlight while exporting enormous mechanical energy. The engine's true output is written in radio lobes, not in optical glamour. Jet duty cycle matters as much as peak power, because building a giant is a marathon rather than a sprint. A short, bright outburst can make a compact radio galaxy with strong hotspots and dramatic inner structure. A longer, steadier phase can inflate lobes gradually, producing a giant with faint edges and a core that may look modest. The same total energy delivered over different timescales produces different morphologies, and the sky preserves those differences. When we see a giant, we are seeing not just power, but patience. Recurrent activity complicates the map further, and the complexity is visible when we look carefully. Some radio galaxies show evidence of multiple episodes, with inner lobes nested inside older outer lobes, like ripples from repeated impacts. The footprint becomes a layered fossil record, where size measures not one moment, but a history of restarting engines. In such systems, the outer lobes can be ancient, while the core has recently reawakened. The galaxy is not a single event. It is a sequence of phases, each leaving a different kind of imprint. This is why the chapter must keep the tone exploratory rather than declarative, because every size claim is tied to a tracer. Every tracer has an aging curve, and every aging curve depends on environment, magnetic field strength, and particle acceleration history. The question is not only how far the jet reached, but how much of that reach is still visible. When we name a record, we are naming a visible record, not necessarily a physical maximum. The universe may be building structures that our instruments still cannot fully reveal. Now connect the jets to their environment, because the footprint is not passive, and the consequences are not cosmetic. As jets propagate, they drive shocks, inflate cavities, and stir turbulence in the surrounding medium, and those disturbances can persist long after the jet fades. They heat the gas and can prevent it from cooling, extending the feedback story beyond cluster cores into intergalactic space. In X-ray images of some systems, cavities align with radio lobes, showing where the jet has displaced hot gas like a piston. The radio map is therefore also a map of work done on the universe. Jets also transport cosmic rays, relativistic particles that can diffuse and stream along magnetic fields, and their presence changes the pressure balance of the gas. Those particles can contribute pressure, alter gas dynamics, and seed extended non-thermal halos that are difficult to detect directly. A single galaxy can therefore export a population of high-energy particles into volumes far beyond its stellar confines. Over time, those particles can interact with gas and fields, subtly influencing how the medium evolves. The jet is not just a beam, it is a delivery system for an exotic component of the universe. Magnetic fields are another exported ingredient, and their significance is easy to underestimate because they are invisible. Lobes carry ordered fields, and as they expand, they concede magnetization in the intergalactic medium, providing structure for future particle motion. Over time, mixing and turbulence can spread that magnetization, making the jet a contributor to the universe's large-scale magnetic ecology. The fields can also affect how later shocks propagate, and how cosmic rays are confined or dispersed. In that sense, a radio giant is a tool for distributing magnetism across cosmic distances. The consequence is that a radio giant is not only big, but causally large, and that causal reach is what makes the term giant feel earned. It changes temperature, pressure, and field structure in regions that would otherwise evolve more quietly, guided mostly by gravity and slow accretion. The galaxy becomes an architect of its environment, not by gravity alone, but by injected energy and organized fields. The lobes are the visible skin of that intervention, glowing faintly where particles still have enough energy to speak. The silence beyond them may still carry the imprint, even when the radio fades. This connects back to the documentary's central question about what size reveals, and it clarifies why radio giants belong in the same conversation as stellar halos. Stellar halos tell us about mergers, stripping, and dark matter scaffolding, because stars are traces of assembly history. Radio footprints tell us about black hole feeding, spin, magnetized plasma, and the ability of energy to travel through low-density space. Both are histories written into extended structures, and both are shaped by selection effects. The difference is that one history is made of stars, and the other is made of fields and relativistic particles. It also forces a comparison between two kinds of boundaries we have been treating separately, and the comparison is not comfortable. The halo boundary is about what remains bound and where light can be traced, which is already a slippery question. The jet boundary is about where energy has been deposited, even if nothing is bound there in a stellar sense. One boundary is gravitational and slow, while the other is electromagnetic and fast, yet both create extended maps around a galaxy. If we accept one as size, why do we hesitate with the other? The two boundaries can be wildly different for the same galaxy, and that mismatch is what makes radio giants feel like a reversal. A host might be a fairly normal elliptical in starlight, with a modest effective radius and an unremarkable halo that fades into the background. Yet its radio lobes can extend across group scales, making the galaxy's influence enormous while its stellar body remains ordinary. The galaxy's centre becomes the most important part, not because it holds the most mass, but because it can launch a coherent process. The visible host becomes a seed, and the radio structure becomes the bloom. This is the chapter's core reversal, and it lands best when we let the viewer feel the scale rather than merely hear it. We expected the largest galaxies to be the ones with the most stars and the biggest halos, because starlight is the most familiar tracer. Radio giants suggest that the largest structures tied to a single galaxy might be non-stellar, transient, and defined by plasma physics. They are built by episodes, not by accumulation, and they can fade even while the galaxy remains. The largest galaxy might therefore be a story about processes, not possessions. Now tighten the observational logic so the viewer can trust the escalation, because the numbers must feel earned. Radio maps measure flux density across the sky, then convert angular size to physical size using redshift distances and an assumed cosmological model. Optical spectroscopy or photometric redshifts anchor the host's distance, which anchors the conversion from arc minutes to light years. The measurement is straightforward in principle, yet fragile in practice, because misidentifying the host shifts the entire scale. A giant is only a giant if it belongs to the galaxy we think it does. Uncertainties enter through identification and projection, and both uncertainties are stubborn. The host assignment can be ambiguous if multiple galaxies sit near the midpoint, especially in crowded fields or along filaments. The true three-dimensional size can exceed the projected size, yet the projected size is what we can measure robustly. That means the record we quote is often a lower limit, not an absolute extent. The universe may be offering us giants that are even larger than they appear. There is also a subtle bias toward finding nearby giants first, and it cuts in two directions depending on the instrument. Nearby lobes cover large angular sizes, which can be filtered out by some interferometric configurations that lack short baselines. But nearby systems also have higher surface brightness per beam for a given physical emissivity, making them easier to detect when the instrument is configured appropriately. Survey strategy therefore matters, because the same object can be obvious in one map and invisible in another. Discovery is sometimes a matter of matching the telescope's listening range to the size of the signal. LOFA and similar arrays are effective because they combine sensitivity to diffuse emission with wide field coverage, and they do so at frequencies where old plasma still glows. They can detect low-frequency, steep spectrum lobes that older surveys missed, and they can map them across large swathes of sky. They also produce polarization information that helps confirm synchrotron origin and field structure, strengthening the physical interpretation. When polarization vectors align across a lobe, the map becomes more than a contour plot. It becomes a diagram of ordered magnetism. That is the kind of evidence that turns a faint smear into a coherent structure. Even with these tools, analysts must fight confusion noise and background sources because the low-frequency sky is crowded. The sky at low frequency is filled with faint radio emitters, and unrelated sources can masquerade as parts of a giant's lobes. Separating a giant's diffuse lobes from unrelated background structures requires careful morphology, spectral index mapping, and consistency checks across frequencies. Sometimes the bridge between lobes is barely detectable, and the case rests on symmetry and probability. The giants demand not only sensitivity but restraint, because overinterpretation is always a risk. Now return to the definitional crisis, because the chapter is not only a catalogue of extremes, and it must not end as a scoreboard. If Porphyrion spans 23 million light-years in radio plasma, do we call that the galaxy's size, or do we call it something else? If not, what category does it belong to, and why do we draw the line where we do? The question sounds philosophical, but it is anchored in physics, because different components obey different rules. A boundary drawn in gravity is not the same as a boundary drawn in magnetized plasma. One answer is conservative and familiar, and it has the comfort of textbooks and clear definitions. A galaxy is the gravitationally bound system of stars, gas, and dark matter centered on a potential well, and that is a physically meaningful object. Jets are outflows, and outflows are not the galaxy, even if they originate there, because they are not bound and they do not orbit. In that view, Porphyrion's lobes are evidence of activity, not part of the galaxy's body. The galaxy remains the host, and the lobes are its consequences. Another answer is more unsettling, and it matches how people intuitively use the word size when they look at a picture. If a structure is produced by the galaxy's central engine and remains connected in a physical causal chain, then it feels like part of the galaxy's footprint. The galaxy becomes defined by what it can build, not only by what it can hold, and that definition has its own logic. We do not separate a volcano from its lava field when we talk about the volcano's reach, even if the lava is no longer part of the mountain. The jet is the galaxy's eruption, and the lobes are the cooled flow. The documentary can hold both answers at once because the tension is the point and the series has been building toward it. In Chapter 3 and 4, the edge blurred because stars and gravity overlap with the cluster, and ownership became contested. Here, the edge blurs because energy and plasma extend far beyond any bound stellar system, and influence becomes a measurable geometry. The universe is offering us multiple kinds of belonging, each grounded in a different physical principle. Our discomfort is a sign that we have been using one word, size, for several different ideas. The escalation also reframes earlier comparisons, and it does so without undoing them. IC 1101's debated halo reaches millions of light years, but it is faint starlight that may be shared with a cluster and shaped by tides. Porphyrion's reach is tens of millions of light years, and it is non-stellar plasma that may be shaping the intergalactic medium through shocks and magnetization. Both cases dissolve a clean definition, but they dissolve it in different directions. One dissolves the galaxy into the cluster's gravity, while the other dissolves it into the web's emptiness. Both cases dissolve a clean definition, but they dissolve it in different directions, and that contrast is instructive. IC 1101 dissolves galaxy into environment through shared light and shared potential, making the boundary a matter of binding and history. Giant radio galaxies dissolve galaxy into environment through exported energy and long-lived magnetic structures, making the boundary a matter of causality and persistence. In one case, the galaxy's edge is where stars become indistinguishable from the cluster. In the other, the galaxy's edge is where the jet's signature becomes indistinguishable from background noise. Now build the chapter's final climb toward the series climax, because the implications reach beyond records and into worldview. If jets can persist across a significant fraction of a cosmic void, then a single galaxy can imprint itself on the cosmic web. The web stops being only a scaffold for galaxies and becomes a medium that galaxies can actively remodel through feedback. We often speak as if the web shapes galaxies, and it does, but radio giants remind us that galaxies can push back. The relationship is not one way, and the evidence is written in faint, enormous lobes. That idea changes the emotional scale of the central question, because it changes what we mean by largest. The largest galaxy might not be the one with the widest halo of stars, or the most extended envelope of bound light. It might be the one whose black hole has written the largest signature into intergalactic space, even if the host looks modest in starlight. The record holder might be a galaxy you would overlook in an optical catalogue, yet it would dominate a radio atlas. The universe is telling us that appearance and impact are not the same measurement. At this point, the chapter's tension sharpens into a single question. Are we measuring an object, or are we measuring the reach of a process? And do we have the courage to admit the difference? If the process is long-lived and coherent, the boundary between galaxy and environment becomes a matter of philosophy backed by physics. The radio lobes are not a metaphor, they are energy and magnetism occupying real volume. When we call them part of the galaxy, we are choosing which physics we want the word to honour. The chapter ends by tightening the suspense rather than resolving it, because resolution would be dishonest to the evidence. We can list sizes in light years, but we cannot avoid choosing what counts, and every choice has consequences. If a radio footprint spans tens of millions of light years, then the phrase largest galaxy becomes a boundary problem again, only louder. The giants do not merely break records, they break categories. They force us to ask whether our definitions are describing nature or simply describing our habits. From here, the documentary pivots to the rulebook we have been postponing, and the pivot is unavoidable. We will confront competing definitions, from starlight to dark matter to jets, and ask which boundary is physically meaningful in which context. If the universe keeps building structures that ignore our categories, then the final answer may be a set of answers. That is not a failure of science, but a recognition that different traces reveal different truths. A single word cannot hold all the ways a galaxy can be large, and that is the lingering unease we carry forward because it refuses to settle into a neat conclusion. Cosmic size is not a single number because the universe draws edges with different kinds of physics, each with its own fading curve. Stars fade, halos overlap, and jets reach into spaces that were never meant to have owners. When we look at a radio giant, we are not just seeing a galaxy, we are seeing the reach of a central engine and the quiet admission that our maps define our monsters. The storylines converge here, because largest galaxy is not one claim, and it never has been. It is 4 different measurements, each tied to different physics, different data, and different failure modes. We can keep the mystery and still build a rulebook if we admit what each ruler counts and what it quietly ignores. Start with the uncomfortable premise, because astronomy begins where intuition breaks. Galaxies do not have edges like planets, and clusters do not have edges like walls. Their light thins into the background, their halos overlap in projection, and their outer matter is more probability than boundary. Even the word edge is a compromise between nature and measurement, because our instruments impose thresholds. In practice, the record we announce is often a record of detectability, not a record of nature. A deeper exposure pushes the boundary outward, and a different wavelength redraws the map again. The universe does not change, but our contour lines do. That is why 2 honest papers can quote 2 honest sizes for the same galaxy. Define the problem in one sentence and then let it expand in the viewer's mind. Largest can mean the widest distribution of stars, the widest diffuse stellar envelope, the widest dark matter halo, or the widest AGN footprint. Each definition answers a different question, and each one can crown a different winner. The confusion is not an error, because the word largest is doing too much work. There is also a historical reason this persists. Early galaxy catalogues were built from photographic plates, where what you saw was what you measured. Size meant a bright ellipse on glass, and the sky background was a stubborn limit. Modern astronomy inherited that language, even as it gained the ability to see fainter structures that the plates could never hold. First definition is stellar extent, meaning the visible body above a chosen surface brightness level. This is the classic textbook size because it resembles a photographed object with a recognizable outline. It is also the most fragile definition because the edge depends on sky subtraction and scattered light. A tiny bias in the background can erase a halo or invent one. Surface brightness is a cruel metric because it punishes anything spread thinly across the sky. Light from a galaxy's outskirts is diluted over large angles, and it competes with air glow, zodiacal light, and the instrument's own internal reflections. Even space telescopes face diffuse backgrounds, because dust in our solar system scatters sunlight into a faint sheen. So the edge becomes a negotiation with noise. In the visuals, imagine a deep optical image that slowly stretches its contrast. At first, a galaxy looks compact and confident, with a bright core and smooth contours. Then the stretch deepens, and faint ripples appear like smoke around a candle flame. Keep stretching, and the smoke becomes a haze that seems to merge with everything nearby. Apply that ruler to IC 1101, and the story feels straightforward for a moment. Its bright central body is enormous by optical standards, often quoted around hundreds of thousands of light-years across. Under this definition, IC 1101 competes with the biggest ellipticals, and it feels like a galaxy in the familiar sense. It has the visual authority of a record holder. But even here, the measurement is not as simple as a diameter on a ruler. Elliptical galaxies do not end with a cliff, because their stellar density declines roughly as a smooth profile. Astronomers often describe that decline with Cercic models, which fit how brightness falls with radius. The size then depends on which isophote you choose and which model you trust. Apply the same ruler to Alcyonius and Porphyrion, and the headline begins to wobble. In starlight, their hosts can look ordinary, with sizes that do not match their radio fame. Their optical bodies can resemble typical massive ellipticals, sitting quietly at the centre of their environments. Under stellar extent, they are not record holders, and the superlative collapses. That collapse is instructive, because it reveals what the first ruler really measures. It measures where stars are bright enough to stand out from the sky, not where the galaxy's influence ends. It is a definition built for cameras and catalogues, and it remains useful because it is repeatable. yet it is not the whole story. Second definition is the diffuse stellar halo plus intracluster light, the faint envelope that deep imaging can reveal. This is where IC 1101 becomes controversial, because the faint light can extend to multi-million light-year scales. The number sounds definitive, but the membership of that light is not. The deeper we look, the more ambiguous the ownership becomes. State the cluster complication clearly, because the viewer needs a mental model. Brightest cluster galaxies sit inside a sea of stripped stars that belong to the cluster potential. Those stars were torn from smaller galaxies by tidal forces, harassment and mergers over cosmic time. The BCG envelope and the intracluster light blend smoothly in projection, especially in the densest cores. In visuals, the cluster core is a crowded city seen at night from above. The BCG is the brightest downtown, but the surrounding glow is not a single neighbourhood. It is light from countless disrupted systems, smeared into a common haze by gravity. The deeper the exposure, the more the galaxy and cluster appear to merge, offer a practical boundary that sounds physical, not cosmetic, and then show its cost. Call the galaxy's stellar halo the stars gravitationally bound to the galaxy's potential, not merely centered on it. Call intracluster light the stars unbound from any single galaxy and orbiting the cluster as a whole. That boundary is conceptually clean and observationally brutal. Explain why it is brutal without losing cadence, because the brutality is the point. Binding depends on the total mass profile, including dark matter and the cluster background. It also depends on stellar velocities we can barely measure at those radii, because the light is so faint. The transition can be gradual, and the data are sparse where the ambiguity matters most. Even the word bound hides complexity, because gravity is not a simple on-off switch. A star can be loosely bound, wandering on an orbit that reaches far into the cluster potential. Another star can be temporarily captured, then stripped again by a passing galaxy. The boundary is a region, not a line. Bring IC 1101 back under this second definition, and let the uncertainty carry weight. If much of the multi-million light-year glow is bound, IC 1101 becomes a stellar giant beyond normal intuition. If much of it is intracluster light, then the largest galaxy label is partly a category error. Either way, the measurement teaches us how clusters recycle stars. This is also where cosmological dimming becomes a quiet antagonist. Surface brightness fades with distance in a way that scales steeply with redshift, making the faintest structures vanish first. What we call intracluster light nearby might be invisible in a similar cluster farther away, so the record can be biased toward the local universe, where faint halos are easier to see. Now place Alcyonius and Porphyrion under the same second definition, and the contrast sharpens. Their stellar halos are not known to approach their radio spans, and deep optical limits often stop far inside. Under diffuse starlight, they remain normal galaxies with extraordinary engines. The ruler selects a different physics, and the winners change again. The second ruler also forces a deeper question about identity. If a star was born in one galaxy, stripped in a merger, and now orbits the cluster, what does it belong to? Is a galaxy defined by where stars are today, or by where they formed? The universe does not label its particles, so we invent categories that only mostly work. Third definition is dark matter halo size, often expressed as a virial radius like R200. This is the radius where the average density reaches a chosen multiple of the cosmic critical density. It is not a hard edge, but it is a standard boundary tied to collapse and equilibrium. It is a way of drawing a circle around gravity's long-term domain. Explain what this definition probes, because it is less intuitive than starlight. Virial radius measures the region that has roughly virialized, meaning it has settled into a quasi-equilibrium between kinetic and potential energy. In LCDM, halos grow by accretion and mergers, and their outer regions are still assembling. Stars act as traces near the center, but most of the mass is dark. This definition is also a reminder that galaxies are not primarily made of what we see. The luminous part is a small fraction of the total mass budget, and it sits deep in the gravitational well. The halo extends far beyond the bright body, and it shapes how gas falls in and how satellites orbit. Virial radius is the most physically motivated ownership boundary, and it is still a convention. Apply it to IC 1101 with the right caution, because BCGs live in a special regime. As a BCG, its dark matter halo is entangled with the cluster halo, and the cluster's virial radius is vastly larger. If we assign the cluster halo to the galaxy becomes absurdly large by definition. If we separate them, ICL 1101's own halo is still huge, but not cluster-sized. The separation is not just semantics, because it changes the implied formation story. A cluster halo is built from the collapse of a large region of the early universe, while a galaxy halo is built from a smaller patch. The BCG sits at the bottom of the combined potential, like a bead in a bowl. The bowl is not the bead, even if they share the same center. Apply the dark matter ruler to Alcyonius and Porphyrion, and the mismatch becomes illuminating. Their host halos are likely group scale or cluster adjacent, but not tens of millions of light-years across. Under virial radius, they cannot match their radio footprints, because gravity's bound domain is smaller than their causal reach. The mismatch is the point, not a problem. In visuals, imagine a transparent sphere representing the virial radius, enclosing satellites and hot gas. Then overlay a radio image whose lobes stretch far beyond that sphere, like ink released into water. The halo is where matter is bound, while the lobes are where energy has travelled. One is possession, the other is influence. Fourth definition is AGN footprint, meaning the extent of jets and radio lobes above a detection threshold. This definition measures influence, not possession, and it is anchored in energy transport. It is the definition under which Porphyrion and Alcyonius become the giants. Here, largest means furthest reach of a central engine. Make the measurement explicit because radio size has its own hidden assumptions. Radio size is typically lobe-to-lobe projected extent, converted from angle to length using redshift and cosmology. The edge is set by surface brightness sensitivity, deconvolution choices, and observing frequency. The footprint can grow in our catalogues as surveys get deeper. Projection is another quiet complication, because we see these systems flattened onto the sky. A jet pointed partly toward us can look shorter than it is, while one in the plane of the sky can look dramatic. Without a full 3D orientation, the quoted size is often a lower limit. The record is therefore conservative, even when it sounds extravagant. Apply it to Alcyonius, and the scale becomes almost surreal. Its radio structure spans roughly 16 million light-years in projection, implying long-lived collimation and a forgiving environment. Under AGN footprint, it outruns any stellar halo record that we can defend cleanly. The host galaxy becomes a small engine at the center of a vast faint product. The visuals here should feel like a reveal, because the radio map changes the meaning of the scene. In optical light, you see a modest galaxy amid a sparse field. Then the radio contours fade in, and enormous lobes appear like ghostly wings. The universe suddenly contains a structure that was always there, but never visible to the eye. Apply it to Porphyrion, and the number becomes almost hard to hold in the mind. Its radio span, near 23 million light-years, pushes the definition into cosmic web territory. The extent is so large that it competes with the scale of voids and filaments. Under AGN footprint, Porphyrion becomes a contender for largest, even if its stars do not. At this point, the chapter's tension sharpens into a single question. Are we measuring what a galaxy is, or what a galaxy does? That question matters because the four rulers are not merely different units. They are different philosophies of classification built from different observables. One ruler is dominated by photons from stars, another by photons from plasma, and another by gravity inferred from motion. The same object can be small in one sense and enormous in another. Now connect the AGN footprint to cosmic voids and the web, because environment is the hidden co-author. Voids are underdense regions tens to hundreds of millions of light-years across. They are not empty, but they have fewer galaxies and less gas than filaments and walls. Their low density changes how jets propagate and how long lobes remain coherent. In visuals, the cosmic web looks like frost spreading across glass, with bright knots and thin strands. Between the strands are darker basins, voids where matter is scarce. Place a scale bar across one basin, and then place a radio footprint beside it. The comparison is unsettling, because the footprint begins to look like a web feature. Explain why jets crossing a large fraction of a void is startling, and keep it grounded in physics. A void is defined by missing matter, so it offers less resistance and fewer disruptions. That can help a jet stay collimated and expand far, but it also means the jet is writing across an unusually quiet medium. The footprint begins to resemble a structure of the cosmic web itself. There is also a subtle thermodynamic angle, because radio lobes are not just lines. They're inflated bubbles of relativistic plasma, threaded by magnetic fields and filled with energetic particles. Their brightness depends on synchrotron emission, which fades as electrons lose energy. In a low-density region, the lobes can expand with less compression, changing how quickly they dim. Tie the void idea back to the record problem, because records are rarely random. If the biggest radio systems prefer low-density corridors, then the largest footprints may be biased toward environments we rarely map well. The web becomes part of the size story, not just the background. Largest becomes a statement about where the galaxy lives. Now add timescales, because size is time integrated, and time is the hidden dimension. Building a multi-million light-year stellar envelope requires billions of years of mergers, stripping and phase mixing. It is slow growth, with many small contributions that only become shocking when summed. The halo is an archive of repeated encounters. Phase mixing matters here, because it is how chaos becomes smooth. Streams of stripped stars begin as coherent ribbons, then spread along their orbits. Over time, the ribbons overlap and blur into a diffuse glow. The final halo looks serene, but it was built from violence stretched thin. Contrast that with jet timescales, because the engine runs on a different clock. To reach tens of millions of light years, jets must remain active or repeatedly restart over tens to hundreds of millions of years. The engine can flicker, but the duty cycle must be high enough to keep feeding the lobes. In radio, size is a fossil of persistence. Make duty cycle concrete without overspecifying, and keep the viewer oriented. AGN activity is episodic, shaped by fuel supply, mergers, and cooling of surrounding gas. Gas can lose angular momentum and fall inward, then be heated and pushed back by feedback. Some systems show multiple generations of lobes, suggesting stop-start histories. A giant footprint can be one long episode, or several stacked episodes that masquerade as one. There is a reason radio astronomers look for spectral aging, because electrons remember time. As particles radiate, their energy distribution steepens, and the radio spectrum changes. Older plasma can become visible only at low frequencies, where steep spectrum emission survives. That means the true footprint can be larger than what a higher frequency survey reveals. Now address energy and momentum budgets, because influence is not just geometry. The outskirts of a galaxy are weakly bound, and their binding energy is small compared with the deep core. Jets carry enormous energy and momentum flux, and they can do significant work on gas over vast volumes. The footprint is a map of where energy has been deposited. Compare what jets can move to what they usually do move, and keep the distinction crisp. Jets couple efficiently to hot gas, inflating cavities, driving shocks, and stirring turbulence. They can prevent gas from cooling too quickly, changing star formation indirectly. They do not usually pick up stars and throw them outward, because stars are collisionless and not easily accelerated by plasma. Jets reshape atmospheres more than they rearrange stellar orbits. This difference is visible in X-ray images of clusters, where cavities appear like dark bites in hot gas. Those cavities align with radio lobes, linking invisible pressure to visible plasma. The gas is pushed aside, heated and stirred, sometimes out to hundreds of thousands of light years. The stars, meanwhile, keep orbiting as if nothing happened. Use that comparison to clarify why definitions diverge, because the viewer needs a unifying principle. Stellar extent and diffuse halos trace gravity and merger history, because stars move mainly under gravity. AGN footprints trace electromagnetic processes and plasma interactions, because jets act through fields and shocks. Calling both size is valid only if we specify which physics we mean. Now return to the galaxy versus cluster boundary, because it is the chapter's conceptual peak. In a cluster core, the BCG envelope can be partly bound and partly shared. The cluster potential can dominate at radii, where the light still looks galaxy-centered. Our categories break because nature built a continuum. The continuum is not a flaw in theory, but a feature of hierarchical assembly. Clusters grow by absorbing groups, and BCGs grow by cannibalizing satellites. Each merger deposits stars at different radii, depending on the orbit and mass ratio. Over time, the outer light becomes a palimpsest, written and rewritten by gravity. Offer the best available operational approach, and let it feel like craft rather than magic. Use kinematics where possible, looking for a transition in velocity dispersion and orbital structure. Combine that with traces like globular clusters and planetary nebulae for sparse outer regions. Add weak lensing and X-ray mass profiles to estimate the underlying potential. Each tracer has a personality, and the viewer can sense the detective work. Globular clusters are bright beacons that survive disruption, and they can be counted far from the centre. Planetary nebulae provide sharp emission lines, letting us measure velocities where the continuum is too faint. Weak lensing uses background galaxies as a grid, revealing mass through subtle distortions. Admit the limitation without weakening the narrative because uncertainty is part of the suspense. Even with all tracers, the boundary can remain model dependent because the transition is not sharp. The faintest light is hardest to measure, and the outermost velocities are hardest to obtain. The largest claim can shift as methods improve. Now confront selection effects directly, because records are made by surveys, not by nature. Deeper optical imaging reveals fainter halos and more intracluster light, expanding stellar sizes. Lower frequency and higher sensitivity radio arrays reveal older, larger lobes, expanding AGN footprints. The record holder is often the first object we could finally see. Explain the record holder problem as a structural feature of astronomy and make it feel inevitable. We search with finite sensitivity, finite resolution, and finite sky coverage. That means the extreme tail of the distribution is undercounted until technology catches up. The title, largest ever found, is almost always temporary. There is also a human bias toward what is easy to publish. A dramatic structure that appears in a new survey becomes a headline, while a non-detection becomes a footnote. Yet non-detections define the limits that make the detection meaningful. The record is a product of both, even if only one makes the news. Apply that logic to IC 1101 and keep the ambiguity alive. Its claimed multi-million light-year envelope depends on pushing to extremely low surface brightness. As techniques improve, other BCGs may reveal similarly vast outskirts, or IC 1101's envelope may be reclassified as cluster light. The record is a moving target because the boundary is. In visuals, show two reductions of the same deep image, each with a different sky model. In one, the outer halo looks expansive and continuous. In the other, the halo shrinks, and the cluster background takes over. The viewer sees how much depends on careful subtraction, not on imagination. Apply the same logic to Alcyonius and Porphyrion, and emphasize the role of frequency. Their discovery was enabled by surveys sensitive to diffuse steep spectrum emission. As arrays improve, we may find even larger systems, or we may extend known lobes beyond current contours. The record is partly a function of what frequencies we listen to. Radio interferometers also have a practical limitation, because they can miss very large-scale emission. If an array lacks short baselines, it can filter out diffuse structure, making lobes look smaller than they are. Calibration choices and imaging algorithms can change the apparent edge. The footprint is real, but its measured boundary is negotiable. From here, the documentary pivots to the rulebook we have been postponing. We stop asking for one number, and we build a taxonomy of size. State the taxonomy cleanly, and keep it usable in the viewer's memory. Size by stellar extent is about the bright galaxy body and observational thresholds. Size by diffuse stellar halo is about accretion history and the galaxy cluster boundary. Size by virial radius is about gravitational collapse and dark matter architecture. Size by AGN footprint is about energy transport and environmental permeability. Then add one more layer, because a taxonomy is only useful if it predicts confusion. The first two definitions are light-based, and they are vulnerable to background subtraction and projection. The third is mass-based, and it depends on modelling and cosmological conventions. The fourth is process-based, and it depends on sensitivity, aging, and orientation. Each ruler comes with its own kind of humility. Now show how the taxonomy resolves tension without erasing wonder, because the goal is clarity, not deflation. ICL 11.1 is a contender under stellar and diffuse halo definitions, with the cluster boundary as the central uncertainty. Alcyonius and Porphyrion are contenders under AGN footprint, with duty cycle and environment as the central uncertainties. Under virial radius, none of these objects is tens of millions of light-years across, and that contrast teaches restraint. Restraint matters because language can mislead even when numbers are correct. A 23 million light-year radio footprint does not mean a galaxy made of stars that wide. It means a black hole has affected plasma across that distance, and the environment allowed the effect to persist. The galaxy is both smaller and larger than the headline suggests. bring cosmic voids back as the chapter's eerie hinge and let the image linger. A jet that spans a significant fraction of a void's radius implies both persistence and emptiness. It suggests that the largest footprints may be built where the universe is thinnest. The biggest reach may require the least resistance. That observation invites a quiet question that hangs in the narration. How many giant footprints are invisible because they lie in directions we have not surveyed deeply? How many are too old, their electrons cooled below our detection bands? The cosmic web may be filled with faint ancient signatures of engines we have not yet recognized. Now place frontiers in extra-galactic astronomy as the practical path forward and keep the momentum. Low surface brightness imaging pushes the stellar boundary outward and tests sky subtraction limits. Weak lensing maps dark matter without relying on light, and it clarifies which potential dominates where. Next-generation radio arrays expand sensitivity to diffuse emission and recover missing large-scale structure. Low-surface brightness work is as much about discipline as it is about hardware. It demands careful flat-fielding control of scattered light and honest treatment of systematics. The reward is a view of the outskirts, where galaxies reveal their past interactions. In those outskirts, the universe looks less like a set of islands and more like a tide. Weak lensing adds a different kind of visual, one built from statistics rather than photographs. Background galaxies become a field of tiny ellipses, each slightly distorted by intervening mass. By stacking many shapes, astronomers reconstruct a mass map that does not care whether stars are present. It is a way of seeing the invisible scaffolding. Radio frontiers, meanwhile, change the story of time as well as size. Lower frequencies reveal older plasma, and higher dynamic range reveals faint edges that were once lost. Better calibration reduces artifacts that can masquerade as structure. Each improvement turns the radio sky from a sparse catalogue into a textured landscape. Name the direction of travel without listing every facility, and keep the tone mysterious. Better detectors, better calibration, and wider surveys will keep changing what counts as detectable. Multi-wavelength campaigns will tie stars, gas, and dark matter into one consistent model. The boundary of the known expands because our instruments expand. Connect this to space exploration in the broad sense, as a human extension of measurement. We do not physically travel to these galaxies, but we extend our senses through observatories. Each new band and each deeper survey adds a new definition of edge. The universe becomes larger in our maps because our maps become more honest. Now, return to the emotional core, because the climax must land in the viewer's mind. Human intuition expects objects to be bounded and comparable, like cities on a map. The universe offers gradients, overlaps, and footprints that are not made of matter we can hold. We can understand the physics and still fail to picture the scale. In visuals, let the camera drift from a familiar galaxy image to a faint halo, then to a lensing map, then to radio lobes spanning a void. Each layer is a different truth, and none cancels the others. The viewer feels the mind stretching, not just the image. That stretch is the real subject of the chapter. Reframe the central question in its final form for this chapter, and let it sound like a tool. When galaxies grow to absurd scales, largest is not a trophy but a diagnostic. It tells us whether we are seeing merger-built stars, cluster-shared light, dark matter's gravitational domain, or black hole-driven influence. The meaning changes, and the change is the lesson. Hold the mystery in the last beats, because certainty would be false. There may be halos fainter than we can currently subtract from the sky. There may be radio lobes older than we can currently detect against confusion noise. There may be systems whose true sizes are hidden by projection, distance, and the universe's own dimming. Even the winners we name today may be placeholders for objects not yet recognized. A slightly different environment, a longer duty cycle, or a quieter void could produce an even larger footprint. A deeper optical campaign could reveal a halo that changes the ranking overnight. Records in astronomy are often just the visible crest of a deeper distribution. The chapter ends by tightening the suspense rather than resolving it. With definitions clarified, the universe still refuses to give us a single edge. Set up the final chapter's resolution path, and keep the promise modest but firm. We will choose which definition answers which question, and we will say what we can claim responsibly. We will also admit what remains unknown, because the biggest objects are often the hardest to measure. The climax is not a number. It is a new way to think about scale without losing the awe. We can answer the central question now, and the answer is deliberately unsettling because it refuses a single clean number. The phrase largest galaxy depends on which component you measure, because galaxies have overlapping physics-defined boundaries that blur into their environments. If you mean the largest distribution of stars and diffuse stellar envelope, IC 1101 remains a leading contender in the modern catalogues. If you mean the largest galactic influence written into space, Porphyrion's radio structure becomes the contender, traced by lobes that dwarf most familiar scales. Both are real and both are measurable, but they are not the same kind of size. At this point, the chapter's tension sharpens into a single question. Are we measuring a galaxy's possessions, or the reach of the processes it launches? Start with the familiar ruler, because it is where intuition still tries to stand and still tries to feel safe. Starlight feels like substance, and it feels like the galaxy itself, because it is made of long-lived matter you can imagine holding together. In images, stars look like a coherent body, a luminous island against blackness, and the mind wants that island to have a shoreline. But shorelines are a human metaphor, and galaxies are not built for metaphors. A galaxy is an evolving distribution of mass, energy, and angular momentum, and its visible edge is often just the place where our instruments lose confidence. When we say outer halo, we're often naming a region where the surface brightness drops below a few dozen magnitudes per square arc second, and the sky itself becomes a competing signal. IC 1101 sits at the heart of a rich cluster, where gravity collects matter into a deep shared potential that belongs to the cluster as a whole. In that environment, the galaxy is not isolated, and it cannot be understood as a closed system with a private boundary. It is the endpoint of repeated mergers, stripping, and long-term accretion, played out over billions of years in a crowded gravitational arena. Visually, the scene is deceptively calm. You see a smooth elliptical glow, almost featureless, with no spiral arms to advertise motion, and no dust lanes to suggest recent chaos. Yet the calm is the afterimage of violence, because the cluster core is where orbits intersect, where satellites are captured, and where stellar systems are dismantled into a shared haze. Its central body is enormous by optical standards, and its outer light can be claimed far beyond typical ellipticals when deep imaging is used. The controversy is not whether the outskirts exist, because the faint light is detected repeatedly with modern techniques. The controversy is whether the faintest outskirts belong to the galaxy, or to the cluster, because the cluster itself produces intra-cluster light that can mimic a galaxy's envelope. That ambiguity is the signature of hierarchical growth, not a failure of measurement discipline or a lack of rigor. In LCDM, structure grows bottom-up, meaning small halos form first and later assemble into groups and clusters through mergers. Clusters grow by absorbing groups, and brightest cluster galaxies grow by cannibalizing satellites, so the outer envelope becomes a blended archive of many origins. This is why CD galaxies were recognized as special long before today's surveys, because observers noticed their extended halos and their central dominance. Historically, the CD label was a clue that cluster centers build galaxies differently, and that the most massive ellipticals are not simply scaled-up versions of smaller ones. The outer light is not merely decoration, because it encodes how the cluster assembled and how long it has been dynamically active. IC 1101's size therefore encodes a history of dense environment evolution, written in gradients that are easy to miss at first glance. Dynamical friction drags massive satellites inward, converting orbital energy into heat in the surrounding background of stars and dark matter. Dry mergers add stars without rebuilding disks, so the remnant stays smooth, while its radius and stellar mass climb steadily. Tidal stripping spreads stars into intracluster light that still looks galaxy-centered, especially when the galaxy sits at the bottom of the cluster potential. In simulations, the boundary between outer halo and intracluster light is not a wall, but a transition in binding energy and orbital families. Some stars remain tightly bound to the central galaxy, while others roam the cluster on long looping trajectories that only appear centered in projection. Dark matter is the quiet scaffolding that makes this possible, and it also complicates ownership because it does not shine. The galaxy's halo overlaps the cluster halo, and the combined potential sets the orbits for stars, globular clusters, and hot gas. At large radii, binding becomes a gradient, not a binary label, because the energy needed to escape changes smoothly with distance. Even our best operational definitions stay conditional at the edge, and the documentary must say that without apology. Isophotal radii depend on surface brightness thresholds and sky subtraction, so a small change in background modelling can move the edge outward by tens of kiloparsecs. Kinematic separation depends on sparse traces and uncertain mass profiles. Because measuring velocities that far out requires globular clusters, planetary nebulae, or integrated light at the limit. The deeper we look, the more the boundary becomes a probability statement rather than a line you can draw with confidence. A star at a given radius may be more likely bound to the galaxy than to the cluster, yet the probability can be close enough to 50-50 that the label becomes a choice. That is the quiet collapse of intuition, because the universe answers with statistics instead of certainties. So IC 1101 is largest in a specific sense, and that specificity is the honest version of the claim. It is among the largest stellar systems by extended light and halo, especially when you include the CD envelope that swells into the cluster core. It is also a reminder that cluster centers dissolve the idea of a clean galaxy edge, because the cluster is a larger organism that shares its matter. To help the eye, imagine the visuals as the camera pulls back. The bright central ellipse remains, but then the exposure deepens and faint light blooms outward like fog around a lighthouse. The galaxy seems to grow as the detector grows patient, and the largest label begins to feel less like a trophy and more like a question. Now pivot to the other ruler, because it breaks intuition in a different direction. The radio giants are not built by accumulating stars, and they do not need a huge stellar body to become enormous in extent. They are built by exporting energy, and they advertise what a central engine can do to the space around it. Alcyonius and Porphyrion show how a supermassive black hole can turn a galaxy into a long-range engine that operates across intergalactic distances. Accretion and magnetic fields launch jets that stay collimated over immense spans, even as they thread through tenuous plasma. The lobes are synchrotron-bright plasma, not bound stellar structure, and their glow is the signature of relativistic electrons spiraling through magnetic fields. Historically, radio astronomy forced this conceptual shift, because early maps revealed structures far beyond optical galaxies. The discovery of jets and lobes made it clear that galaxy can mean more than starlight, and that invisible processes can dominate a galaxy's footprint. In that sense, the largest radio galaxies are heirs to a long tradition of surprises, where new wavelengths redraw the universe. The host galaxy can look ordinary in optical light, and that ordinariness is part of the lesson we are meant to absorb. The record is not set by stellar mass alone, because a modest-looking elliptical can still contain a black hole capable of sustained power. The record is set by jet power, duty cycle, and the emptiness of the surrounding medium, because the jets need time and room to expand. Porphyrion's span pushes the concept into cosmic web scale, and that is why it feels like a boundary problem rather than a simple measurement. The lobes trace where energy went, not where matter remains gravitationally owned, and the distinction matters. The edge is defined by detectability and particle aging, not by an orbit, and that makes the boundary feel more like a fading echo. Radio size is also threshold-driven, and the documentary must say that plainly because the audience deserves the mechanism. The measured extent depends on frequency, sensitivity, and imaging choices that recover diffuse emission, especially at low surface brightness. A deeper low-frequency map can extend the boundary outward, just as deeper optical imaging can extend a halo, and both expansions are real but conditional. Under the hood, the physics is precise, even if the boundary is not. Synchrotron emission depends on magnetic field strength and electron energy, so the same plasma can look bright at one frequency and nearly invisible at another. Interferometric arrays also filter out very large, smooth structures unless the observing strategy and data processing are tuned to recover them, which means size can be limited by technique. The lobes also fade with time, which makes size time-dependent in a way starlight is not. Electrons lose energy through synchrotron radiation and inverse Compton scattering on the CMB, steadily sliding down the energy spectrum. Older plasma shifts to lower frequencies and can slip below survey limits, so the visible structure becomes a snapshot of a changing distribution. That means Porphyrion's measured size is a visible footprint, not necessarily the full physical footprint that the jets created. Some of its plasma may be present but silent at our observing bands, and some may have mixed with the surrounding medium until it is indistinguishable. The record is always a record of what still speaks, and silence does not guarantee absence. Environment decides whether a jet becomes merely large or truly gigantic, and this is where the cosmic setting becomes part of the engine. Dense cluster gas can bend, disrupt, and confine jets, turning them into distorted shapes and limiting how far they travel before dispersing. Low-density corridors and void-adjacent regions can let lobes expand and persist, because there is less external pressure and fewer shocks to shred them. In visuals, this contrast is dramatic. In one case, jets look like bright, compact plumes pressed against a thick atmosphere, with the lobes that seem trapped. In the other, the lobes inflate like vast bubbles, their edges traced by faint contours that stretch across a background of distant galaxies. This is where the cosmic web re-enters as more than scenery, because it is the architecture that channels both matter and emptiness. Filaments feed galaxies and clusters, setting up growth by mergers and accretion, and they also shape the density of the intergalactic medium. The same web sets the permeability of intergalactic space to jets, creating pathways where energy can travel farther before it dissipates. Feedback connects the two storylines, and it is the bridge between big and meaningful, because size alone is not the point. In clusters, AGN jets inflate cavities and heat hot gas, regulating cooling and star formation, and the evidence shows up as X-ray bubbles and shock fronts. On larger scales, giant lobes can stir, magnetize, and seed cosmic rays into the intergalactic medium, leaving behind altered conditions for later structure. This is one of the chapter's quieter implications. A galaxy like IC 1101 becomes huge because it sits where matter flows inward, while a system like Porphyrion becomes huge because it sends energy outward. One is built by accumulation, the other by export, and both are natural outcomes of the same cosmological rules. So extremes are not anomalies, even when they feel like they should be. They are signposts of the rules, amplified by rare alignments of history, environment, and timing. Hierarchical assembly produces rare, massive BCGs in deep potentials, and long-lived AGN activity in permissive environments produces giant radio footprints that can outscale their hosts by orders of magnitude. From here, the documentary pivots to the rulebook we have been building across every chapter. Largest is not one claim, and the universe does not reward us for pretending it is. It is a set of claims tied to different physics, and each claim carries a caveat that is not a weakness but a clue. IC 1101 answers the largest by stars and stellar envelope question, with cluster overlap as the central caveat that refuses a crisp edge. Porphyrion answers the largest by galactic influence through jets question, with detectability and aging as the central caveat that makes the footprint time-sensitive. The two answers do not compete, because they occupy different definitions that measure different realities. Now the synthesis must land calmly, because the terror is not in the numbers alone, and not even in the distances. The terror is that intuition wants a ladder, a ranked list that ends with a winner, and the universe offers a gradient. It offers transitions, overlaps, and boundaries that depend on the question we ask. Think in nested scales, not a single ranking, and let the visuals do some of the work. The Milky Way is our familiar disk and halo, a system we can picture without strain, with spiral arms that wrap around a central bulge. Its dark halo extends far beyond the visible disk, yet even that halo has a fuzzy edge defined by models and traces. The local group is our neighbourhood, a few million light-years of shared gravity and motion, where the Milky Way and Andromeda dominate a swarm of dwarfs. Even here, boundaries blur because the local group blends into the larger cosmic flow, and the outskirts are influenced by neighbouring groups. The lesson scales upward because the universe repeats its ambiguity at every level. IC 1101 becomes a continent of stars within a cluster's heart, grown by mergers and stripped light, and the imagery should feel almost geological. It is largest in the slow language of accumulation, where size is history stretched thin across faint halos. Its outskirts are a census of everything the cluster has consumed, and the census is written in low-contrast light that demands patience. Porphyrion becomes a reach across intergalactic space, drawn in radio light by a central engine that does not care what our eyes prefer. It is largest in the fast language of energy transport, where size is a causal footprint rather than a bound structure. Its lobes are the memory of a black hole's long persistence, and the memory is etched into plasma that slowly cools and fades. The quiet conclusion is that cosmic size is a moving target, because our definitions track different processes that do not share the same edges. Stars define one boundary, because they are luminous and long-lived, yet they can be stripped and shared. Dark matter defines another because it dominates mass and gravity, yet it is inferred rather than seen. Jets define a third because they are energetic and far-reaching, yet they are transient and threshold-limited. This does not reduce the wonder, and it does not make the universe less real. It relocates wonder from the comfort of a single number to the deeper strangeness of overlapping truths. The universe does not merely contain big things, because it contains mechanisms that make big depend on what you ask, what you measure, and what physics draws the edge. And that dependence is not a trick. It is a reminder that the cosmos is not obligated to match the categories that evolved in a world of solid objects and sharp borders. When you look long enough and deep enough, even a galaxy becomes a negotiation between gravity, light, and time. The chapter ends by tightening the suspense rather than resolving it. The next record holder may already be in the data, hidden in faint halos or low-frequency maps, waiting for the right method to reveal it. There is a particular kind of mystery in that idea, because it suggests the universe is already larger than our current summaries. Better algorithms will separate galaxy light from intra-cluster light more honestly, using improved background models, statistical classification, and kinematic information when it exists. Deeper surveys will recover diffuse radio emission that current pipelines still filter away, especially when the structures are enormous and smooth. New eyes will find structures that were always present, but never confidently connected, because connection requires both sensitivity and restraint. So the final answer is not a single name, and that is the point the chapter has been building toward. IC 1101 is a giant of accumulated stars in a cluster's core, and its size is inseparable from the cluster that helped build it. Porphyrion is a giant of influence, a galaxy extended by what its black hole can do, and its size is inseparable from the medium it expands into. When we ask for the largest galaxy, we're really asking what kind of universe we live in, and whether our instincts can adapt. A universe where boundaries fade, where extremes are expected, and where scale is not a ladder. Scale is a landscape shaped by gravity, time, and energy, and the landscape keeps going even when our maps end. Across this journey, scale stopped being a number and became a negotiation between instruments, definitions, and physics. We watched the Milky Way's tidy disk dissolve into a vast halo, then followed that same blurring to IC 1101, where faint starlight, cluster tides, and a shared sea of intra-cluster stars make the edge feel like a moving target, and we met a different kind of giant entirely, radio galaxies like Alcyonius and Porphyrion, whose jets and lobes stretch for tens of millions of light-years, turning size into reach, memory, and impact. By the end, the promised rulebook isn't a single ruler, it's a taxonomy of boundaries, each answering a different question with a different kind of evidence. If you care about where the stars still belong to a galaxy, you chase surface brightness limits, Circic wings, and the treacherous art of sky subtraction. If you care about ownership in a cluster core, you need kinematics, globular clusters, planetary nebulae, lensing maps, and X-ray gas, because bound is a gradient, not a line, and IC 1101 may be part galaxy, part cluster, part historical accident of mergers. If you care about the deepest gravitational footprint, you talk in virial radii and overlapping dark matter halos, accepting that even those physically motivated borders are conventions laid over a continuous field. And if you care about influence, you follow jets, shocks, cavities, and magnetized lobes, knowing that radio edges depend on frequency, sensitivity, plasma aging, and whether our telescopes can even see the faintest relics. That is why the biggest claims always come with a quiet asterisk, and why the universe keeps winning our arguments by changing what the argument is about. The largest galaxy by starlight might be an enormous CD envelope that fades into intra-cluster light, while the largest galaxy by influence might live in an ordinary-looking host, quietly inflating lobes across cosmic web corridors. In both cases, the record is partly a physical extreme and partly a mirror held up to our methods, because deeper imaging, cleaner background models, and better low-frequency radio maps can redraw the boundary without moving a single star. So when we ask whether we're measuring a city of stars or the shadow of dark matter, the unsettling answer is that we're often measuring both at once. Largest galaxy doesn't mean one champion with one diameter, it means choosing which edge you trust, light, binding, halo, or jet, and admitting that each edge reveals a different chapter of formation. IC 1101 teaches that galaxies can become indistinguishable from their environments, until identity itself turns statistical, and the outskirts belong to nobody cleanly. And Alcyonius and Porphyrion remind us that a black hole can make a galaxy larger than its own starlight, writing its presence into the intergalactic dark for millions of years. Maybe that's the real terror of cosmic size. Not that the universe contains objects too big to imagine, but that, at the largest scales, the universe dissolves our definitions and asks us to measure reality by the physics that draws its edges. As new surveys dig deeper, and new algorithms learn to separate galaxy light from cluster glow, keep asking what largest is really measuring, because the next record holder may already be hiding in data we've barely learned to see.